the right number of the submissions so that the workshop doesn't look very poor. So we had to do some activity to increase the number, asking for friends and family to submit extended abstracts. And thanks to all of you who basically did this. So I think we now have a reasonably good program. As you might have seen from the program, we do not have the keynote. So this hour, I propose we try to discuss the question that I would be personally very much interested, which is why do we have the situation that the last 10 years, this room on the array workshop is filled with the same faces, but we literally have 0 papers written together. So why is this happening? So do we really hate each other? Or is there something we can do about it? And do we want to do anything about this? I'm kind of far from thinking that we can solve this problem just within this hour, but maybe we can start. And I thought that maybe as just a kind of good starting point, we could introduce ourselves from the perspective that not things that you put on your homepage, but from the perspective, what projects are you currently working on, and what kind of collaboration would you be interested in, right? So the format is that anyone wants, please take a microphone, come to the stage, take 5 minutes, and just describe in very loose terms what are you working on, what are your interests in the area that is somewhat related to arrays. Okay, and then we can discuss. It should be very open. It's not anything formal. So please do ask questions and so forth. So maybe I can start and then just pick some victims some way. Okay, so I'm Artem. I'm assistant professor in the Southampton University, and I'm currently interested in the intersection of type theory and high performance. So my work and my envisioned work has to do with connecting array theories that are encapsulated in dependent types. So that's one big problem. How exactly do you encode arrays within a dependently typed system so that the specifications that you write become kind of beautiful? The proofs that you have to supply when you write these specifications are not horrible. So the encoding of these arrays is a big question, right? So I mean, I do have some answers, but I definitely do not have the final answer. This is one thing that I'm very much interested. And the other thing that is related to this question is, okay, you've written specification, you've proven a bunch of things about it, and then you still want to run it fast. So how do you do this? So how do you translate a dependently typed specification that is kind of array-based into something that runs fast? So what is the ideal backend? What is the ideal translation process that goes well to any language of choice in essence, right? So what is this compilation down to? I don't know. Maybe we can take an existing array language, or maybe we can compile down to C, or I don't know. So the sky is the limit, but the actual mechanics of translation and the properties of translation are very, very unclear to me. So if anyone wants to kind of work on these topics, if you have a very good backend and you want to try out interesting problems that are generated from the high-level specification to test whether your backend actually can generate really high-performance code, I'm very much open. I'd be interested. Or if you have an idea what invariants of an array specification are very difficult to observe in a non-dependently typed system, I'm happy to work on this too. So if you have some very annoying mistake that always pops up, maybe you can lift it into invariant and just make sure the type system rules out it entirely, and you'll have kind of a formal. All right. that's me. Um, Maybe anyone else?
I'll be brief. I'm Mary Sheeran from Chalmers. One of my main interests has been hardware description and verification, and my current obsession is ways of folding up circuits over both space and time. So I've always been interested in higher order functions. I'm a functional programmer, so I've always been interested in higher order functions for various things. But these days I'm very interested in what are the higher order functions for interesting behavior over time, and can we do verification efficiently in that context? That's what I'm interested in. But I am partially retired, so I'm only supposed to be working 40%. So really what I want to do is come and visit you. And get paid by my pension and talk to your students and have fun. So I'm very open to such visits. I have an intern right now. He's not here because he's at PLMW, but he's working on the stuff about folding up circuits, and he's working on FPGA implementation of that and on associated variants of K-induction for verification. And he's looking for a PhD position. So if any of you have PhD positions in PL systems, whatever, talk to me and I can introduce you to Victor because he's fantastic. Oh, good.
Morning. Are we on? Yeah. Okay. Good morning. First time. It's my first time here, so it's good to see all of you. Closer, even closer. All right. Good to see all of you, and look forward to meeting everyone. I have a side project. One thing that I'm working on that's not related directly to what I'm presenting today is doing formal verification very quickly. There's this particular system called MetaMath. It has an extremely simple specification for the language, and it has a database of about 250,000 proofs written in this particular specification. I wrote a parser just really quickly to ingest the database. But I'd love to take that entire database and verify it in underneath the threshold of human detectability. So, like 100 milliseconds, 200 milliseconds, right? And I've talked to Aaron about this. Maybe we can use Codifunds and push it off onto the GPU or something. But if any of you have no details about doing unification or some of these verification algorithms very quickly, I'd love to talk to you. Thank you.
Hey, I'm Max, and my main job here is helping out with the video production process. But my day job is a professional APL programmer at BCA Research. We have a third of 300,000 data sets that I help maintain and sanitize. So at work, I write in a more traditional style, since I work with one other APL developer who I want to let him understand my code. He's a lot older than I am. But for fun, I like writing point-free code, just super crazy tacit one-liners for fun. And I've noticed some interesting things as I created these tacit expressions.
What did you say? You have a data set?
We have a database of economic data that our researchers use to publish reports on the global economy. That's it.
Hello, my name is Troels. Most of my work has been in the context of the FUDOC programming language, which is an array language that compiles to GPUs. My current research interests are there's two things that I think might be possible areas where collaboration is possible. One is, well, many areas could be possible. These are the most obvious ones anyway. One is I'm really interested in the consequences of the implications of language design on how you express various programs in different data pro languages, and also what the implications are for performance. So I'm basically open to anything that involves taking some array language and doing some kind of experimental study in it. Another thing, a research project that we've just started up, me and my a PhD student we just hired, who will present here today but isn't here yet, is just looking at the different steps in a classic compiler, which I'm thinking like an ML compiler, and figuring out how do we do each of these steps in a data parallel way. Now, some of the parts have been studied before, like Aaron has done a data parallel compiler. And we start also by looking at parsing, but particularly things like unification is also specifically something that we intend to look at. We haven't gotten there yet, so I don't really know what the answer is, but I mean, that is definitely a possibility for collaboration, because I am very interested in figuring out how to do union find and such in a data parallel, highly efficient manner.
Hello, I'm Thomas and I work at Radboud, and I'm interested in generating code for distributed systems, so clusters from array languages. So I will also be presenting a layer that you can target with array languages, but it is still pretty rudimentary. It already shows some promising results, but it does not support all hardware from clusters and also no GPU memory yet. So I would like to re-implement this in a lower level library such as UCX to support these things and improve performance. So if someone is also interested in generating code for array languages, then I would like to collaborate on that.
This close, or do I need to like really eat the mic? Okay. So I'm Aaron Su, and my broad interest is really in the usability of and the theory of usability of programming languages as humans interact with them. So that's my interest. And so I got into APL and array languages primarily because the interaction paradigm in practice at scale was so different than other programming languages. And so that's really kind of where I would like to explore things more. Is we have all these ideas and we've got lots of theory about the mechanics of a particular thing, but we've got really, really weak theory about how to even ask how good a given language design is for humans to use and why it might be good, and you know, the psychology of that, the whole HCID of programming languages, really.
Sorry for coming late. Very good morning. My name is Clemens Grelk. I have been working most of my life on the language called single assignment C that Thomas already mentioned. And so the purpose of that is to have one language, a data parallel array language, obviously, for some talking here, to compile to all these various multiple compilation targets that are of interest, from GPU to multi-core to clusters and so on. Single source, multiple targets, and then have a highly optimizing compiler that exploits the functional semantics of single assignment C. Otherwise, the language looks very different from other functional languages because it has a C-like notation. Why am I here? I recently moved after 15 years of Amsterdam to Germany, and I'm building up a new research group. So if you are interested, well, I see mostly older chaps here, but if you are interested, if you know someone who's interested in starting a PhD in this greater topic, then let me know. Thank you very much.
Hi, my name is Cosmin Wancea. I'm from University. The mic. Okay. So my name is Cosmin Wancea. I'm from KU, University of Copenhagen. And I also have been involved with Trolls on Futark. My main interests are essentially optimizing compilers and optimizing parallelism to the degree that you get state-of-the-art performance. And of course, also into having a high-level language that can express higher-order constructs that have richer semantics, and then how do you make use of that richer semantic in order to better optimize your programs and so on, raising the level of abstraction at which the compiler reasons. And so this is the big theme, but I have various projects that I'm interested in. For example, with Nikolai and Robert, we are working on trying to verify array properties such as permutation of and partitioning and boundedness and this kind of thing in the context of a data parallel array language like Futark. And things here are a little different, as Nikolai has a talk, in the sense that, like here you are having many fine-grained operations that are always producing arrays, and it's mostly you are performing many such operations on an array of indices, and then you get some final indices at which you want to scatter the values, so it's a little bit different than the sequential or task parallel context. Yes, so mainly I'm interested in any kind of compiler optimization, but also a little bit on the language level languages and such, and transformation, program level transformation, such as automatic differentiation and such.
Hello, I'm Ivo from Utrecht University. I'm in the last year of my PhD. I'm working on Accelerate, which is a parallel array language embedded in Haskell. And I've mainly been working on the runtime and trying to reduce the overhead at runtime. I'm also interested in the overhead compared to sequential programs. So I talk about zero overhead parallel scans, which are as fast as sequential scans later today. And I talk about our new scheduling algorithm. So that's all about CPUs, but I also want to do similar things with GPUs. But I'm also at the end of my PhD, so I don't have that much time for it.
Hello everyone. My name is Juuso Haavisto, and I was thinking that I could maybe talk a little bit about how I even ended up studying this stuff, since you started about asking that why is there collaboration or no collaboration. I was thinking that maybe it would be a nice idea to tell a little bit about how I ended up studying array programming languages at Oxford. So before I applied to do my DPhil there, or like a PhD, I also considered Northeastern, where they have the Remora language, and then I also considered here in University of Copenhagen for Futhark. But then I read that my supervisor, Jeremy, had written this paper I understood very little about. So I felt like something that I knew the least of. I wanted to get into that kind of like environment. And I think that is also like a good way to describe a little bit about maybe the approach or the background that Jeremy and I have at Oxford, which is a little bit more about maybe defining these array programming languages in some manner.
Hello everyone, my name is Nikolai. I'm a PhD student with Cosman, as he already introduced me. I work on this mechanical proofs for Futhark, which I will present today with Cosman. But I also work more on an applied side. So I really enjoy using these languages, for example, for machine learning, or I've been working on time series decomposition and so on. Experiencing the pains of using them, then I'm also maybe a guy to talk to. No more volunteers?
I can say, well, if there's nobody else,
introduce himself.
Some folks in this corner, do you want to say something about maybe? It doesn't have to be a lot, as you prefer. Just tell us what interests you.
Chance to introduce myself. So yeah, so I'm Yudai Tanabe from Tokyo Institute of Technology. So my favorite, my expertise is type theory and
Closer. Yeah,
closer. Yeah, so yeah, my expertise is theory of type programming languages, and so I'm interested in the implementation aspect of the programming language. So I joined these workshops. Thank you.
Right, so we're not really working on much. We're just here because we made a master's
degree, and now we have decided to present what we made. But our interest is more on the, what do they call it, process calculus? We have trying to implement arrays in the process calculus, also based on Futhark to some extent. So yeah, not much working on. We present that. That's all three of us. I think more of a final hooray trying to get it out there. So not at the moment, at least. It is more just to see, okay, what can we actually do something with this? Is anyone interested? Or yeah.
All right, thanks very much. It's quite interesting. Maybe amongst things that we now know roughly who's up to what. Is there any? Let's discuss whether there are some technical obstacles why we do not have this papers together. I mean, would it help if we create something like, I don't know, a Zulip server for arrays, like there's one for, I don't know, category theory and for types. Would it be helpful if we have something where we could post things and get replies? Yeah.
To actually promote collaborations and such. Well, this is. Can you hear me? It's a small room, right?
We don't need. Okay. It's for. But anybody's listening.
For the recording.
Oh.
Yeah, fine.
So, okay, can I sit here or should I go there? Okay, so we are. So just 2 words. So we had a lot of fun by having a collaboration between like 5 different languages or 4 different languages, Accelerate, APL, DACE, Futhark, and am I forgetting? SAC, sorry. Huh?
You said had. It's still an ongoing project. Has something happened?
No, we have. Yeah, we are having a lot of fun doing a comparison between language and performance about across these 5 languages. And it has been a lot of fun because we have to develop benchmark and implement them and so on and so forth, right? And then I'm involved in another similar collaboration in which with Mary Hall and Ari Rush and such, and we are looking to write essentially a taxonomy paper on scheduling languages. And that's, essentially literature review and, trying to give a direction for future past research and so on. But it's a lot of fun. And discussing this kind of issues bring forth new ideas that you can continue to collaborate with that group on whatever comes out from that project. And this is an easy way and very pleasant way to start collaborations.
But the question is, how do you find out if can I join this paper on
well, this one it's kind of
no, I'm
close to, but definitely next ones. So my concrete suggestion would be, like, if you find here various opportunities for collaboration, like people who are interested in the same kind of things, for example, dependent types or I don't know what else, right? And you can start writing either a taxonomy paper, like an easy way to start collaborating with a concrete result. It's either a comparison paper or so this is
but
this has come up for some.
I think to me this sounds a bit too late. So the question is, okay, I mean, once a year we meet in this room, that's fine, and then we can talk. But there's another 364 days when something else is going on, and it would be nice to probably have some connection, not only on during the array. So.
But I think the one of the reasons for meeting here is to actually find overlapping themes on which several people are interested.
Sure.
And it's also another connection. It's like I really enjoy these working workshops. Okay, maybe array is not the place because it's not a working workshop, right? But these are the thing in which you have presentation until midday and then you have joint work. And there you can start more easily collaborations and such. So one of the papers, the one on scheduling languages, came from one such working workshop, essentially.
I have a little, is this thing even on? Yeah. All right. Well, so I have a little pet theory that I've noticed of why it might be difficult to do collaboration right now, is in a lot of other research fields, you have sort of a very established unified base of technology that everybody can center around. And in some ways, array programming is really old, and in other ways, it's really immature in respects to a sort of emerged de facto standard of where you would try ideas out, right? So you've got like APL interpreters, you've got APL compilers, you've got dependently typed systems, and all of these different implementations, the full stack is essentially independent, and for pretty good reasons, because it's very difficult to merge all these stacks together right now. Whereas in other programming language spaces, there's a pretty well-established way in which you can communicate to each other and do collaborations over, a pretty wide range of topics on a single platform, I guess. And so I think part of what we struggle with is a lot of our research would have to be comparative or taxonomical at the moment, just because the platforms are very difficult.
But isn't
to
that
unify.
kind of a chicken and egg problem? So
Yeah.
I mean, we could have, if we were to start discussing things, right? We probably could overcome all these issues. The one of the problems is that we do not speak to each other by some reason.
Yeah, potentially. Yeah, I think that's true.
So what, do you have good examples that would fit? Right. But the idea is to let's organize ourselves such an array working workshop. All right. Yeah. They're also much cheaper than PLDI'24. That's true. Okay, so in essence, you're saying that we could make more events like this in order to meet more often than once a year. Okay, that's very good. More focused. Like you have like 5 days. Yeah. In which you want half of the day to actually collaborate. Yeah. This is just presentation. Sure.
Yeah, I think I would completely agree with Aaron. So, 2 things. First of all, I think it's not as bad as you said, because we have this workshop for a couple of years and it's lively. That's an achievement, right? It could have been a one-off or two-off thing and then it dies out, particularly over pandemic. So now we're still here, we fill a room more or less. So I think that's a good sign as well.
I mean, you missed my initial point, but my initial point was, yes, exactly. We do.
Yeah, you want to go beyond that. I got that. But I think it's also nice not just to say, oh, how bad are things, but it's not as bad. We are here, right? This could be worse than this. And the second thing is, I think I completely agree with Aaron that one of the I would say, in a sense, obstacles. I'm not saying we are able to change this, but we all work on kind of different programming languages. They all have their particular niche or so in the wider area of array programming. And of course, that precludes, let's say, technical collaboration in the sense that it adds something to my compiler or so. I think that's really difficult. And can we change this? I don't think so. On the other hand, if you look at others.
volunteer their time to make that happen. I'm done. Thanks.
Oh, okay. Is it worth trying? Shall we think about something like this, or what do people think? Or it seems completely alien and it's a waste of effort. But what do you guys think? I mean, it's pretty easy to set up, right? Yeah, but I mean, would it be useful if anybody kind of sees themselves using, or it's just another stuff that sits in the corner? I would certainly join.
I mean, how successful it's going to be, you only find out by trying. But I think it would be a good idea to have probably something like a persistent representation, that we could represent ourselves as a community. We already have a name for it. And we have an annual workshop, and we have maybe a mailing list and maybe a tiny website with just lists a few pointers to, let's say, active projects, something like that. Job offers, if you want. These kinds of things. I think that would be relatively little effort to create. But I completely agree. It requires one or two people to actually pursue it, to tell people that give me your URL to link, something like that.
Instead of a chat server, I'm really old school, so I definitely would prefer a mailing list.
Me too.
Oh, I'm done.
You're done. No, you're not done.
That's even easier to set up. So, okay, shall we do this? All right. Okay. Let's discuss this as we go. What exactly are the details? Okay.
Or you can put a pointer to this workshop, for instance, say we have an annual workshop, couple of pointers to projects, people involved, blah, blah, blah.
Yeah,
I think you can hack a website in a couple of hours. And
more technically, where this is going to be hosted.
does it matter?
It does, because somebody has to do this.
Yeah.
And we better, make sure that the server that supports this mailing list doesn't die, tomorrow.
So this is a very nice initiative, right? And I'm sure it's going to be very useful for various purposes, but I'm not sure how much is going to influence collaboration. In my experience, collaboration either appear naturally, or you lock some people in a room and you say you don't get out until you find some common topic on which you want to collaborate. Okay, this thing with mailing list, I mean, I do not read all the messages from the mailing. I don't have time for it, right?
Well, that's a very good option, but I'm afraid that this is illegal these days, right? To lock people in the room and wait till they give you some.
How if they opt in first?
Yeah, if they're, there are masochists there might be willing to be locked in the room and such.
Array escape room. I think most of us are academics here, right? So for us, the currency is a publication, right? So we are kind of driven. Surely we want to achieve something, but we also think very much about whether you can wrap this project as a publishable thing. So sure.
one more thing, Robert. So for the quality of the recording, yes, as
Hello? Okay. Yeah, I'm Robert. This is work done in collaboration with all these people. Oh, I'm sorry, I immediately forgot. I'm Robert. This is work done with all these people at the University of Copenhagen, as well as Magnus from Aarhus. And I believe they're all in the room right now. I don't know about that. No. So the context of this is that this is done in Futhark, which is a functional array language. It's designed to study the compilation of array languages, and there's a few important things that you need to know about it for this talk. First of all is that space is function application. Functions are curried, which means that every function really only has one argument. So f of x, y, z means this thing with the parentheses. And it has a Hindley-Milner style stack type system, which means it has parametric polymorphism. And as an example of a Futhark program, this computes the dot product. You can see that all the function applications is just when done with the space. And yeah. So what is rank polymorphism? So if you have just normal scalar addition here, 1 plus 2 equals 3, the idea is that we can lift that addition operator to work on higher dimensional inputs. So here we have 2 vectors, 1, 2, 3, 4, 5, 6, and it adds them piecewise. And it will also, here you can also add a vector and a scalar, and it will replicate the scalar appropriately to add it to the vector. And it's not just for infix operators, it also works for functions. So here we have square root applied to this matrix, and it does it piecewise in the obvious way. So to summarize what that all means, it's roughly, rank polymorphism is roughly the ability to apply functions to arguments with different ranks than the function actually expects. And the benefit, at least in our context here, is that it makes code easier to read, and it more closely matches the math that you're trying to describe with the code. So for example, map plus is not as readable as just putting the plus in its proper infix location without the sort of administrative map that we have there. And also in practice, basically every popular rank polymorphic language is dynamic, so it's very uncommon to have this feature with a static type system, especially with parametric polymorphism, because those things all make it hard to do. So some background about some functions that we'll use in this talk. There's map. I'm sure everybody here knows about map, but mapping, you take a function and you apply it to every element of some input array in the obvious way. And our map here can also take many arguments for for functions that take more arguments. So plus takes 2. So you give it 2 arrays, and it does the obvious thing. So the first element here is the first element of each array added together, and so on. And then rep corresponds to replicate. But the unique thing here is that we don't actually describe how long the replicate array should be. For this talk, we just sort of ignore that issue. In actuality, Futhark can actually do some size inference and figure out how long this thing should actually be. But we're not going to talk about that. So just don't worry about how long the array should be. So for an example of how we can do rank polymorphism with map and rep, if we are trying to add this matrix here to the scalar, what we first do is we have to lift the scalar to also be a matrix. So every rep adds a dimension. So we rep twice. And now we have some 2-dimensional thing on the right. We don't know exactly the length, although it will, in this case, it will match the matrix. And then we have to also lift the addition operator here with maps. And then this whole thing will then to every entry here, we'll add a 1 using this elaboration. Of course, it's not just for infix operators. It works for any kind of function. So here we have some input XSS, which is a matrix, and we have some function, which has that type. It takes a vector and a matrix and gives you an integer. And then we want to make f of XS rank correct. So what we first do is we first map the first application, because it's being applied to a matrix, but it expects a vector, so we can map with the function. And then we have to also rep the second argument, because this map has, in a sense, inflated the dimensionality of the function. And so we have to overcome that with this extra rep, essentially. And you can see that with the type of map of fxs here. And you might think, well, you don't really want this rep. And in practice, you don't actually need it, because many reps like this that you need because of previous maps can be fused away. So you can often get rid of these maps, these extra reps by fusing them into the function by doing this lambda expansion right there, eta expansion. So our goal to make rank polymorphism work in Futhark is to essentially insert these maps and reps automatically, and to make the function application rank correct. And there are a few challenges involved with this. The first one is that there's ambiguity, so there's often many ways to do this elaboration that are in a rank correct way. So here's an example where we have sum and length, and we're applying these things to a matrix. One possible rank correct elaboration here is we first take the length of the matrix, which of course gives you a scalar, but sum expects an array or a vector, and so this is no longer rank correct, so we have to insert this rep here to make this thing work. Many of you probably think this is kind of a gross elaboration, and the actual one that you would probably want is this one, where you map the length over the matrix and then you sum up those. But of course, there's in fact infinitely many ways to do this, because you can always insert extra reps to overcome maps and keep doing this forever and ever and ever. So in this case, there are actually infinitely many ways to actually make this thing rank correct. So the question is, how do we choose? And to choose, we've invented two rules here. And the first one is that we say that an application can be mapped or repped, but it can never be both. And so just as examples of things that are okay. So in this first example, obviously you just have a map, so it's okay. In the second example, you have two reps, that's okay. You can have any number of reps, you just can't have both map and rep. And in the third example, you might think that's not okay, but the point is that the h actually takes two arguments here. So in the first argument, then the first application is just h to x, so we've just mapped it twice there. And then in the second application, which is to y, there we've repped it. So that's also still okay. But what isn't okay is mapping and repping in the same application. So here f is just applied to x, so it's considered the same application, and that's illegal. And also in the second example there as well. And the point is that it's never necessary to map and rep in the same application, because you can always get a rank correct program without doing this. So it's an easy way to disambiguate possible, or to eliminate possible elaborations. As the second rule, our goal is to minimize the number of inserted maps and reps. And we found that, in general, this aligns with what the programmer actually intends to do. And it's a simple mental model. It aligns with what the programmer actually intends, generally, because you don't intend to insert superfluous maps and reps yourself. You tend to do the minimal possible thing to make the thing work. The minimization happens over every single application in a top-level definition. So it's sort of a global minimization over each definition. And the reason why Rule 2 also helps us with ambiguity is because you want to choose from the minimal possible elaborations. So if we go back to the sum of length of XSS, there's only two possible minimal ones. And they're minimal because each one inserts a single rep or a single map. And so we've whittled it down, to just these two choices. Of course, you still have these two choices. So in this case, Futhark would actually say, send an error and be like, wait, I have these two possible choices, you have to choose. And a challenge, again, is that this minimization process is global. And it also, every application requires you to consider, so in sum, for example, here, when we're considering how to elaborate length of XSS here, we only know to map it because there's an outer sum. So to know how to map the inner application, we have to also consider the outer application. So you can't do things locally. You have to consider all the applications at once. And that's also another challenge. Okay. So yeah, you have to consider all applications simultaneously. And another challenge here is that, of course, Futhark has parametric polymorphism, which means that functions can have type variables. And the problem with type variables is that they can have any rank, so you don't know anything about them. And so the question is, how can you statically insert these maps and reps in the presence of these type variables whose ranks you do not know? And to begin answering these questions and how we solve these challenges, let's look at constraints. This is a constraint-based system. If we're just looking at a function application, so here we have some function, it takes some parameter type P, it has some output B, and it takes some input with type A. And we're looking at f applied to x here. In a normal application, we just have the constraint P has to equal A, right? To apply the function, the parameter type has to equal the argument type. We only care about rank, of course, so we relax this requirement to say that the rank of P has to equal the rank of A. And this double bar notation just means the rank, or the number of dimensions that the thing has. So just as an example, this is the type of matrix, so dimension, integer, so it's a matrix of integers, and of course that has rank 2, and just integers is a scalar, it has rank 0. So, of course, rank polymorphism means rank indifferences are allowed. So how do we encode this? And what we do is relax our constraint further. And there's two cases. In the first case, this is when the parameter type has a rank that's lower than the argument type, and this corresponds to a map. So what we do is we introduce a rank variable here called M for map, and that accounts for this difference between the rank and the parameter and the rank and the argument. So if we're looking at a square root applied to this vector here, we get this constraint here. So this integer here corresponds to what the square root expects. It expects a scalar, and that has rank 0. But we've applied it to a vector, which has rank 1. And then we have this equation, and from that equation, we can solve that m equals 1. And that means that we need a map to make this thing rank correct. So from this constraint, we've deduced that that a rank correct elaboration here is put a map in front of the square root. Similarly, in the other case, when your parameter type has higher rank than the argument, we introduce another rank variable, r for rep, and we play the same game. Here we're using length. I know length itself is a little bit of a funky thing in terms of repping, but ignore that. So just look at the constraint just to understand. So if we're applying length to 3, we're going to have to rep that 3. And an important thing here is that now, because length itself has a type variable, we get a type variable in the actual constraint. And of course, you don't know what the rank of this thing is. You just know that it's some type variable. So that just persists in the equation. And what happens is that then r can be any value. There's infinite many solutions here because of the rank variable, because that rank variable can assume many different ranks. So what happens is that this constraint means that we have infinitely many different possible elaborations here. Thanks. So if we take all that together, of course, when we apply a function to an argument, we don't know if we should map or rep statically, right? So we have to include for the possibility of both. So we include both an m and an r in our rank equation. But of course, rule 1 says that we can't map and rep. I mean, together we can only do one or the other. So that means we have to add additional constraint here, which says that either the m is 0 or the r is 0. And then the way that this proceeds is that we go through a top-level definition, and we generate these constraints. So this one, these two right here, for every single function application. Just to show you how this works, if we're looking at sum, so this is two different functions, right? Sum of length of some matrix. We first generate the constraints here for length, just as we did before. And then we also generate the constraints for sum. And notice here also that sum, the m1 from length also appears here in sum. And that shows that how you choose m1 will affect how you choose the rank variables for sum. So the whole thing, different applications affect different applications in this elaboration. And of course, rule 2 says to minimize the number of maps and reps, right? So let's also encode that. And exactly the number of maps and reps is exactly these variables, right? And now it's starting to look a lot like an ILP. There's just one problem, which is that these OR constraints are not linear. But you can play some ILP magic. I won't go into it here, and you can linearize them. And so that's what we do. And so we get this ILP. And so the TLDR of how this whole thing works then is that for every application, we generate a rank equality and rule 1 constraint, which is the OR constraint. We can transform the constraint set into an ILP and solve, so exactly this thing. And then we use our ILP solution to elaborate the program with the implicit maps and reps. So here, for example, if your ith application in this program, which is f of x, and we saw the ILP says that m sub I should be 3 and r sub I should be 0, then of course you insert 3 maps and you don't insert a rep. And then you have an elaborated program that is rank correct, not necessarily type correct. And you just take this thing and you continue with compilation, and the rest of the compilation pipeline has no idea about rank polymorphism whatsoever. So how does this look for the user? Map and rep are nothing special. They're normal Futhark functions. The programmer is free to write both of them in their source code. And what this means is that the programmer can use automap to whatever extent that they wish. So if they don't want to use that at all, they just use explicit maps and reps wherever, and there's no inference at all. If they want to use it somewhat, they can make some things implicit and some things explicit. Or if they want to use it maximally, they make everything implicit up to ambiguity. And on the note of ambiguity, so we saw this example before with sum of length. In this case, we cannot decide which one to choose, right? So what we do is we trigger an error, but our error can be exactly this message. It can say sum of length of blah, blah, blah can be elaborated into these two possibilities. We can give it as explicit feedback statically to the user. And then disambiguation is very easy because these things are just normal Futhark functions. The programmer can just insert a map or rep themselves into the program. And of course, it's fully transparent because the compiler can always elaborate any implicit program into an explicit one. So you as a programmer can always say, hey, what does this program actually look like explicitly, and the compiler can tell you exactly what it's doing. So the practical impact of this, it's hard to exactly quantify because it's just syntactic sugar, right? What we did, though, is we took our benchmark suite and we rewrote the programs in it to take advantage of automap when we thought it would increase clarity. And here's just an example of a program. So this thing is sort of cluttered with all these administrative maps. And it sort of obscures what's actually going on here. But with automap, we can get rid of all of them. We do have to include some reps here, but that's OK. And you can see, like, for example, these QRs and QIs at the bottom are much simpler and are much closer aligned with the math that they're actually trying to express. Some metrics from our benchmarking. So the key takeaway here is that most ILPs that we generate are very small. Some of them, like this 28,000 thing, is kind of big, but that's largely a product of the fact that the implementation is very unoptimized, and we can remove many constraints that are being generated. And even with our very unoptimized implementation, type checking slowdown is about 2.5 times. So it's in practice very usable. For related work, I'm only going to talk about typed systems. There's typed remora, which is a very general and powerful system. And unlike us, they actually express rank polymorphism at the type level themselves. So they bind shape variables here. For example, this could be the type signature of a sum, that can collapse an array of any dimension into a single scalar, which we cannot express in our system. But unfortunately, inference is very difficult and still is an unsolved problem. There's also the Napoleon functor work by Jeremy Gibbons. And this is a rank polymorphism encoding in Haskell, which is also very cool. But it leads to some complicated function types for the user. It also requires a very sophisticated type system with dependent types or dependent like types. And the error messages are potentially not so great. And then, of course, there's single assignment C. This is probably the most popular version of rank polymorphism in a type system. It doesn't have parametric polymorphism or higher order functions unlike us, but it has some cool stuff, especially here, rank specialization, where you can specialize what a function does based off of the rank of the input. And you can do some cool stuff with scans, and you have a paper about that. So in summary, AutoMap, it's a conservative system for, and importantly, it's compatible with Hindley-Milner type systems. So you can sort of add it on to an existing system in a reasonable way, which is what we did. Anything that can be inferred can also be inserted explicitly. So it's very much like a classic type system with classic type inference. You can always choose to put the type and a type annotation yourself explicitly. Type checking is, of course, based on some heavy machining, which is ILP. But the problems tend to be simple, and the solver tends to be quite fast. And we've implemented this in Futhark. It's not really production ready yet, but we're working on it, and we have a little bit of work to do on that. And check out Futhark up there. There's also a blog post that I wrote about AutoMap that goes into all this in more detail. And there's also, you can check out me. And just as a quick ad, I'm looking for a postdoc or a job if anybody has one. And that's it.
Questions?
Thanks for the nice talk. Thanks for mentioning SAC, because I was always thinking, well, we are a statically typed rank polymorphic language. And I wonder a bit why you do this wrap thing. Because we have, in principle, similar problems. And we came up with a different solution. That means we keep the scalars.
Yeah.
And we have basically different versions of these elaborated functions, basically array versus array, array versus scalar, scalar versus array. And that is, for our case, very important to keep this as a kind of recursion termination in the type inference. And I wonder now, why do you blow up a scalar to an array of infinite size that you then bind to the shape of the other stuff? And not only that, I mean, you never want to execute it this way. You only want to, then you have to fuse it away, because otherwise it's terribly inefficient. So why do you do this?
So no, in practice we do what you do. So it is inefficient in practice, because so the reps there are sort of just a helpful thing. In the end, we actually fuse the reps into the bottom of a map, and we actually don't manifest the replication. Yeah, right. So that in practice we actually don't do that. So if you do then this detour? The detour doesn't actually happen. It never gets manifested anyway. We do the detour to express the constraints. Essentially, it was a way to explain the problem in some sense. Is it a complicated way to express the problem? It's the simpler way. It's the more general way. If you don't, otherwise you're specializing for different cases, right? This is a completely general approach, and then it gets optimized into something that's efficient.
Yeah, so if I understand this correctly, if it can find a valid rank polymorphic treatment, it'll apply it, right?
If it's not ambiguous.
Yeah, so there's a space of programming where you would like to be able to say, I'm rank polymorphic in these particular ways, but otherwise, if it's not this particular type of rank polymorphism, I want to give an error. So I can think of, where you might want to handle scalars going up to any arbitrary rank, or maybe vectors applied. But if we've got a matrix and a cube, well, those shouldn't scale up, or something like this, right?
Yeah.
Does this just sort of bypass all of that? And because you could, even if you insert some explicit ones, I think if I understand this correctly, it'll just, if anything's missing, it'll just add it, right?
Right.
Okay.
So if anything is missing, it will. If the minimum solution is there's only one of them, it will just add it, and that's what it will be. In practice, we've found that what you intended is pretty much what happens. Usually, the programs are sufficiently constrained that there's only one possible rank correct solution in that sense.
Is there any way to say, like, to create an error condition where yes, we could have been rank polymorphism here, but we're intentionally not being?
No, but maybe there should be. And of course, you can always explicitly, write what you want without rank polymorphism, right?
Yeah, thank you for the talk. I'm interested if you can have you can think of sort of infinite dimensional arrays as functions as being infinite dimensional arrays, and you want it in mathematical notation, since you're trying to sort of simplify things down and say that your code can represent the underlying math more directly. Like, you might want to perform operations where your inputs are functions, might be functions, or they might be primitive like scalars or something. Can you see a way to extend this to where you're sort of having rank polymorphism but allowing your these functions as infinite dimensional array representations?
I'm not sure I entirely understand, but we do actually support higher order functions, so you can actually automap on functional inputs themselves, but I don't think that's what you're asking.
I'm thinking like you might just want to say like f plus a g,
Yeah.
right? And then whenever you provide an argument, it applies f and g to the argument, for example, and then just adds them or something.
Yeah.
Something like that
Yeah.
is what I have in mind.
I don't think we I don't think we support that. We should talk about that after. I don't think I totally understand.
Yeah.
Okay,
We're about out of time. Let's
Yeah.
give Robert another applause.
I think let's take everything off.
Robert will continue like this if you have more questions. Our next presentation is by William, also from the University of Copenhagen, who will talk to us about parallel parsing.
Yeah. Hello. Can you hear me? Okay. Maybe the other way around might be better. So does this work? Good. Okay. So what I will be talking about is some of the theory behind an LLP parser generator that Troels and I have been working on. And most of the theory isn't like ours, but we will still explain the theory because that's that got asked about in the reviews. So so LLP, what is it? It's a subset of LL grammars, which Wagner and Mellicher describes in their paper Parallel LL Parsing. And sorry if I butchered their names, but that is how it's going to be. And so basically what Q and K means in the context of LLP QK is that we have some Q look back and we have some K look ahead. And what we also have in the parser generator is we have some data parallel tokenization, and some of the first descriptions of this is found in Hillis and Steele's data parallel algorithms in their paper. And one of the first descriptions of how data parallel tokenization is done, we believe is found in Vodder's master thesis. And I won't talk about how we create the syntax tree, read Vodder's master thesis. And the actual implementation, it's found in, you can find it on GitHub, and we've decided to call it Alpac. So, and we believe also this is one of the first general implementation of an LLP parser, because there was some minor problems with the theory, which had to be solved before we could implement it. Okay. So why do we want this? Because we want to write fast parsers for the GPU. Next slide. So this is a definition of a total deterministic final automata. And so we have some Q states, which are finite, and we have some symbols, which are a set of symbols, which we call sigma. And we also have a transition function, which takes a symbol, a state, and returns a new state. And this is specifically a curried version, and that will become useful. And we also have an initial state and a set of accepting state. So normally when we want to do some lexical analysis, we have a sequence of symbols. And what we do is we apply the transition function to the first symbol and the initial state, and we get a new state. And we use this state from before in the transition function together with the symbol and get a new state. And we keep going until we arrive at the last state. And then we have to assert that this state is in this set of accepting states, right? Yeah. Okay, but we can rephrase this in another way. And we do this by, once again, having a sequence of symbols. And then we partially applied our delta function, our transition function, to every symbol. And then we just compose them all. And then we get a single function, which we just apply to our initial state. And then we just assert that is in the, what is called the set of accepting states. Why is this useful? Well, you may have guessed it. Data parallel reduce and data parallel scan. So we can use this to compose all these functions in a fast manner, and then we arrive at a single function at last. So the important thing here is we need an efficient representation of these delta function, because if we just do the composition and still have to do some computation in the end, then we haven't like won anything. We have to like do the what is it called? Sorry. we have to do some work while we do the composition. So, and representation we can choose is we can decide to have delta functions, which maps the state to state, and we can represent it as an array. And as you see, normally the function could take some state 0 and map it to 1, and take 1 and map it to 0, and 2 and map it to 1, and then we can represent it as an array like this, where we use the indices. But this is not that good because it's very inefficient. It ends up scaling with like the number of states. Give me a second. So how do we solve this? What we do is we pre-compute all the compositions. So what we have to do is we have to create all these delta functions, and then we have to like do all the permutations with replacement. And then we just enumerate all of these, and then we can create a table so we can do like index lookup into it and then get the state. So we don't actually have to compute these the individual states, but we can just look at the overall, what is it called? The overall, like the data functions, yeah. But we also have to do this in a smart way, because else we're gonna end up with a very big number if we just do all permutations with replacement. So we only consider the ones which are like next to each other. Symbols that can follow each other are the ones we consider. So now I will talk a bit about what happens when you do this. So if we consider a small JSON subset with some strings and numbers and other stuff, then we have like about 14 states, and the table becomes 153 times 153 sized composition table. So what happens when we add symbols like null, true, and false? Well, we get 17 state, and the table becomes 1,000 by 1,000. So it grows very quickly, I hope you see. And it's also kind of problematic that it's like, it takes up a lot of space if you want to cache it. So it's not that great, but now it's hopefully you have an idea how data parallel tokenization works. Now hopefully you're gonna get an idea how LLP parsing works. So we're gonna start off by considering an example. So we have a grammar which produces like an even amount of parentheses on each end, and this is the LL parsing table we use for it. And so now I'm just going to introduce a bit of like a quick example with some notation. So if you want to pass open close bracket, then the first element of this tuple is the input. Then we have the initial pushdown store, and we have an empty sequence of production. So here are the productions. Then we look up in the table, and we see that we have to expand it, and then we do a derivation, and then we add this to the stack based on the table, and we get a production over here. And another thing I forgot to mention, this is like a relation that says this can passes into this using LL parsing. And then here we have a pop, and then it removes the first element. So we keep going like this. We do a derivation here, and until we arrive at the end where we have an empty input and an empty pushdown store, and then we have our productions. So what we see here is we have a transition function which takes this state to another state. So the idea we want to do now is we kind of want to use kind of the same trick as we did using parallel lexical analysis. We want to take this transition function, find an efficient way to represent it, and then we want to do sort of a composition. But we arrive at a problem actually, which is that a pushdown store is unknown for a given symbol. So these when you are at a specific symbol, you don't know the previous pushdown store at all. So you have, they are dependent on each other when you're doing this sort of parsing. So the intuition behind what we do is we consider a string, a substring xy, where y is the look ahead and x is the look back. Now we just assume that parsing went well. We're just going to assume that. So here we have y, where a is the first symbol of our y, and we have some pushdown store a, and then we keep on passing until a is gone, and we arrive at a final pushdown store. And we also have to assume something about we popped the last element of x, or some pop, or we pop some element from previously. And now we want to find the pushdown store such that it is the shortest prefix of all the possible pushdown stores. So if we look here, this is a valid for the symbol. If you have look back, this parenthesis, and look ahead, this parenthesis, then this is a valid pushdown store, and you can derive it to this. But the one below in green is actually a prefix. A is a prefix of this one, so this one is shorter, so we choose this one. Another thing is, because we had the condition about popping element here, then this one isn't valid. And I think I would be honest and take this slide with a grain of, I was not done, sorry. Also, so now what we see, if this is possible, then we are able to map xy to an initial pushdown store, a final pushdown store, and some productions. And I would take this slide with a grain of salt, because if it may be the case that I have, what is it called? It's fumbled the theory, because this is the actual definition we end up using. There's also an algorithm to finding this described in that paper. Also a minor thing, we changed this, which is the problem in the paper. And also Wagner found this. Okay, good. So the thing is, now I want to show it in action, hopefully. So we start by augmented grammar, adding these two symbols to each end, and then here are the exact definition of each tuple element, and here we see that the look back is here and the look ahead is here. And as you see, you can, as an example, find the two parentheses here as an tuple element, as a state. Now, the problem is we want to resolve, like, we can't do composition in the same manner. Okay, good. We can't do composition in the same manner as before, so we do this. Sorry, I lost track of thought. Give me a second. Gotta reset. So now we want to do is we want to check that if the parsing went overall well, and this is done by sort of like a composition again. So we do this using parallel bracket matching. So we map we look Q back and look K ahead for each element in the input, as you see, and we want to do it on this input. We also add these brackets. Good. And then we get a bunch of different states here. What we do afterwards is we just remove the productions and we save them for later, because if it went well, then we can just glue them all together, actually. So what we do afterwards is we reverse the final pushdown store, and we want to do this because we want to like check if the future states matches up or the previous. So then we also like remove this one state and we add some parentheses to make it clear that we want to do bracket matching and we want to do like typed bracket matching. So here we see all the brackets matches up, and we can do this very fast. And here are the production sequence. So we were successful in checking that this input could be passed. Okay, now another reset. Okay, so here are some benchmarks. So Pareas is a previous implementation of LLP, but LLP 1.1 only. So not for general Q and K. And what we have here is a JSON parser implementation, and Pareas does a JSON parser, but they can't parse JSON because JSON isn't LLP 1.1. So what they do is they have a larger grammar and they do a bespoke parse afterwards to check that things went well. So what we see here is Alpac. This is also a LLP 1.1, but without the bespoke parse. And we see that it scales just as well as the LLP 1.3 parser, which is the actual JSON parser here. It isn't that detrimental to add like 3 look ahead, actually. So what we achieve a throughput of roughly a little under half a gigabyte on an 800, and this is terrible. Because if you compare it to something like the highly optimized SIMD-JSON parser, then it achieves like 2 to 3 gigabit throughput on a single core. So it's terrible. But I have hope, and I have some implementation of some Lisp lexers. So one of the most expensive things during this is actually during the lexing, we believe, because you have to remove a lot of stuff and you reduces the input quite a lot during lexing. So, so we see a FUTAC implementation here, and it ends up like these 6 gigabytes per second. But if we use COP, this is like an extremely naive implementation, actually. And then we achieve like it gets much better. So I have hope, and yeah. So what we want to do in the future is we want to implement a CUDA backend for Alpac. And the reason why we want to do this is like during the lexing, it's actually something like 4 kernels we end up using to do that. And we should be able to reduce it to a single kernel where we have better I forgot what it's called actually. Write access, I think. Read-write pattern. Okay. So another thing we are considering implementing is an ISPC backend, which would allow us to do to have like write good SIMD code and see if this also actually results in like fast parsing on the CPU. And another thing we have a problem with is the lexer. The lexer, when it does tokenization, it always uses maximal munch, which isn't that nice. So we end up just eating this, and then it fails tokenizing this, which we might want to find a way not to do. Another thing we might want to do is find a way to collapse the concatenations of symbols into a single transition. So null could, if we could find a way to collapse this into a single transition, then we would have less states. Okay. Parsing. So another thing is in Władysław Wagner's PhD thesis, you can find a larger grammar class called LLP star, which would allow us to parse more regular things like regular expressions and such. So a good idea, and it builds upon LLP. So a good idea might be implementing this in the future. Okay, I think that is it. Okay.
Okay, I hope nobody else has questions, because I'm going in. No, so thanks for the presentation. It's very interesting for me. I'm highly motivated around this space. I had one question about how your presentation. You were talking about the quadratic growth of the table states. Is that only for the lexer, or is that, do you use the composition, the tree decomposition of your transitions both for lexing and parsing?
I don't use the tables for parsing at all. The tables, I don't use the decomposition for parsing at all because you end up having like a much nicer representation here. And I think it is more close to exponential, the actual size of the Lexa tables. So it's even worse.
So this is specifically for your parallel lexing implementation?
Yeah, this is specific for parallel lexing.
You don't use this for the parser itself?
No.
Okay.
No, but it was kind of trying to get a red thread or something. I don't know if that's an English term.
Okay, and the whole architecture is designed as a parser generator, so you have a BNF style grammar that then gets produced into stuff. Okay, and you were citing some of the prior work. Do you? I hate to be this person. Do you cite Gunda and Berth's 1984 work?
The 2x2
Yeah,
ABL?
the 2x2.
No.
Okay, is there a reason this is? How does this compare to that work?
I have no idea.
Okay, because in there it looks like you're doing exactly what they do in their parser tables. So I'm very curious to see how the research compares across the two and the way that you express that.
I think Troels had some opinions about it or something. Maybe not.
Yeah.
Yeah, we can wait. We can talk
and,
about it later.
And then finally, you said you're not going to discuss the concrete syntax tree in the talk.
Yeah.
In my experience, generating the actual parse trees from this can be a significant expense. Do you have techniques to ensure that you generate those efficiently on the GPU?
Oh, no, sorry, I forgot to mention that. That is a good point. No, the concrete syntax tree actually makes, like, you can't do it in O of n work. You have to do O of n log n work to create the syntax tree, but it doesn't seem like that is the most expensive part.
Okay. So what techniques do you use to generate your syntax tree on the GPU?
You have to. I don't have any example slides for how it is done, but it's actually pretty well explained in Robin Vodders.
Okay, so you just use Vodders.
Yeah, basically.
Okay, cool. Thank you.
Good.
More questions? Yeah, maybe I could ask a very naive one. So can you explain a little bit of kind of motivation rather than it's an interesting kind of exercise to make your lexing parsing on the GPU? Yeah, but why? Do you want to? I mean, why do you? Is it for performance? Because rarely in the languages parsing is a critical bottleneck that we want to make faster. So what's really the end goal?
Well, I would say I don't feel like I have that specific of a reason, but I guess you can have like a big, like large sets of like data, like your like Parquet or like your JSON, and then you wanna pass this, which might be very nice if you are doing. I'm just gonna move this out of the way. Perfect. Which you might want to do if you're if you have a lot of data. So that would be nice.
Right. Okay.
It's actually not true that parsing turns out to not be a significant cost. There's a ton of business applications where when you do the analysis of where they're spending the time, it is literally all in parsing, and that's so having something that runs this stuff on the GPU can be a major boon to like ETL applications in business.
All right, thanks very much. Let's thank the speaker again.
Our next speaker is Nikolai, and again from the University of Copenhagen, who'll talk to us about something that was one of the original motivations behind array programming, which is doing proofs on them, in this case mechanical proofs.
Yes, hello. My name is Nikolai, and today I'd like to talk about a very much work in progress on doing mechanical proofs in an array combinator language. And as you might have guessed, that language is going to be Futhark in here. Okay, so first of all, what do I mean by mechanical proofs? I mean that specifically we want to be able to prove properties on arrays. And examples are written here, such as that an array is a permutation of another array, that it doesn't have any duplicates, or for example, that it's sorted. So we want to do this in Futhark, and Futhark is a purely functional data parallel language. And with me today, I bring sort of a running example called partition indices. And what this function does, this is sort of the Futhark signature for it. So it takes an array C's that are Booleans of, we call them conditions, of size n, and then it produces an integer array also of size n. What this function does is it will partition the indices 0 through n minus 1 according to these conditions. So if I give it true, false, I get 0, 2, 1, and 3. So I'm able to use these indices later to permute an array according to the conditions. Okay, so what we want to be able to do is put annotations on inputs and outputs in Futhark so that you might be able to prove, for example, that this is in fact a permutation of 0 through n minus 1. And why do we want to do that? Mainly we want to use it to optimize programs, but you can also use it, for example, to verify the safety of parallel writes right here, like scatters, or that you're actually indexing arrays within bounds. And to give a motivating example of this, this is a scatter in Futhark. It takes a destination array as the first argument, then it takes an array of indices, and then an array of values to write at those indices. So the destination here is a bunch of zeros. It's denoted down here, or shown down here, and then we have the indices and the values. And then what scatter does is it writes these values according to the indices. So this is the example from before with the conditions. It will permute 20 and 30 here. So what could we use the fact that we know that 0, 2, 1, and 3 is a permutation of 0, 1, 2, and 3, which is the size of the destination array. We could, for example, use it to know that we are overriding all of the values here. That doesn't need to be the case with scatter. And so we wouldn't need to actually initialize this array. We wouldn't need to write the zeros. So that's one optimization. Another thing is that we can immediately infer that also the output of this will be a permutation not of the indices, but of the array values that we're scattering. Okay, and then finally, sort of more on the safety side, scatter has this thing that if since it writes in parallel, if you give it duplicate indices that write distinct values, so here we're trying to write both 20 and 30 to index 1, it's not well specified what this does since it's run in parallel. So you might want to, for example, show that the indices don't have any duplicates. Okay, so how do we go about doing these proofs? This is sort of a very simplified graph. So we have a program, then we want to generate some kind of queries for proving these properties, and then we want to hand those to an algebraic solver. So before we get into generating queries, which is really what I want to talk to you about today, I have a bit of context on Futhark. You got some of it already, but the array or Futhark programs are essentially compositions of array combinators, and the two most important of which are map, which takes a function, an array, and then applies that function to every element in the array. So here I have map with times 2 on 1, 2, 3, and I get 2, 4, and 6. A bit more fancy, we have scan, which takes an associative binary operator and a neutral element. So here this would be plus and 0, for example. And then an array, and it computes a prefix sum of that. So that's the first element in the first location of the output. And in the second location, you get the first two elements combined, and so on. So here 6 is 1 plus 2 plus 3. Okay. But as I said, Futhark programs are really compositions of these array combinators. So for example, you can write a dot product. I do it in kind of a funny way here because I only show you map and scan. But you can also map binary functions. So in Futhark, you would write map2. And then we can do a scan over that and take the last element, and then we get the sum of that. Okay, so this is to sort of say that the partition indices example that I showed you at first is really just a composition of these maps and scans. So what the function does, or how you implement it, is to first compute all of the indices for which the conditions are true. And then you compute the indices for which they're false. And then you combine this in the last line according to the predicates. I don't show you the false indices here, but trust that they are actually also just maps and scans. What I want you to take away from this slide is that we do bulk array operations that produce integer arrays, and we do them in sort of compositions, and in the end we get often arrays that we will use for indexing, so in a scatter, for example. That this is like a common paradigm of how you write programs in Futhark. Okay, so then we can go a bit into how do we generate these queries. And the first step we do is to model the programs as functions from indices to values. So the simplest one that I can write, for example, is for just an array. Here we have an array x is 1, 2, 3. And then we can sort of say that the domain of this function are the indices, so 0, 1, and 2. And then we can write x as a function of I. So here it's I plus 1. We can also do this for the multiplication example. So here we write it as its own function that takes an array x's of size n and then applies this map to it. So here we see that the domain is now 0 through n minus 1. And the definition of the index function itself references or indexes into x's. Okay, so we have a restriction here that's not entirely obvious. So we only want to model integer arrays with these index functions. And to do this, we find it so far sufficient to restrict the values to what we call sums of products, and here right of terms, where terms are integers, program variables, array indexing, or sums over array slices, so very limited form of sums. And we do this in order to be able to actually prove stuff on it later. Okay, so I want to show you how would we derive an index function for partition indices, for example. And I'm just gonna go line by line and show you. So the first statement is a map with an if statement. So how do we handle this? We put cases on our index function. So this is a piecewise defined function. And this essentially means that these predicates or guards, they must partition the domain, which is 0 through n minus 1 here. And also they must be mutually exclusive. But we get that very easily from an if statement, likely. Throughout constructing these index functions, we also do a lot of simplifications. So one simplification you can do here, sort of to notice that this function is equivalent to just casting the booleans to integers. And so we get rid of cases like this, which is generally a thing we would like to do. Okay, so then we come to a scan, which is a bit more involved. And the way that we represent scans in general is as recurrencies. So we have a base case for I equals 1. This is the first element of the array. And then we have a recurrent case for all other indices. That is the current element in the array being operated on, and then combined with whatever is the previous value of this index function. Here you might notice that now we have a reference to an intermediate variable, t flags, and our goal is really to come up with an index function that is describing partition indices in terms of its input instead. So we want to eliminate this reference. And the way we do this is by substituting functions into index functions into other index functions. So here I want to substitute t flags into t ints. And to do this, we first check that the domains are compatible. Here they are exactly equal, so that's easy. And then we combine all of the cases. So if we have more cases on t flags here, we would just have a combination of those here. And then we can insert the values like this. So we lose the reference to t flags. But what now if we would like to substitute this index function into another? If you do that, then you will just have a reference to t ints I minus 1 still. So one thing you can do is to rewrite this recurrence in terms of the index function that you're substituting into. But Another thing you can do, especially when you have scans with plus, is just to do a sum. So that's another simplification that we do. So hopefully you're convinced here that if you put I equal to 0 in, you will get a sum of only one term, which is C sub 0, and so on. We can continue doing this for all of the program, for fins and for the final statement. And then what we get in the end is an index function that looks like this. And just to convince you that this, what this actually says, this is our true indices from before. And you can sort of convince yourself that if you put an I in here and the condition is true, then the index that you get out is the sum of all the true conditions minus 1 to get an index. And in the other case, if it's not true, you are sort of at position I in your array, but then you shift to the right by the number of conditions that are true that come after you. So this goes from I plus 1 to n minus 1. Okay, so now we also have this annotation that we want to prove a permutation of something. And from this, we can generate a query that says that these two branches are non-overlapping. So the indices that you get from the two branches are distinct. And moreover, there are no duplicates in the first branch, and there are no duplicates in the second branch, and also that they cover all of the domain. So we have, it has to be start at 0 and end at n minus 1. So hopefully that convinces you that we can generate queries for programs like these. What we then do is we hand it to an algebraic solver. And the way that our algebraic solver is kind of naive, it has, how it works is kind of naive. We have an environment of ranges on variables, and then we have expressions wherein we want to eliminate these variables. And I just want to show you that, of course, a program gives you ranges on variables, but these index functions also extend these ranges. So here, for example, you immediately have that I is bounded between 0 and n minus 1. But we also have that, of course, casting a condition to a Boolean to an int bounds its value between 0 and 1. Okay, so we had our query. How do we actually go about formulating something that can be proven here? Specifically to prove this no duplicates, we would like to show that if we have two indices, one being less than the other, then inserting this first index into our branch that we are currently in will lead to a value that's less than if we use the later index. And why do we want to show this? Well, if we can show that why is this sufficient? Oh yeah. So if the value at a later point is always greater than at an earlier point, of course you can't have any duplicates. The way that we encode these ranges for I1 and I2 is shown to the left. So you could say that I1 is less between 0 and n minus 1, and that I2 is between the maximum of 1 and I1 plus 1 and overrounded by n minus 1. And moreover, because we are interested only in this blue case, we also know that this predicate is true for I1 and it's true for I2, which means that this will be 1 for I1, like if you insert I1 in here. And we also put that in the range environment. And then we give this to what we call a Fourier-Motzkin elimination-like solver. What it will do is it will iteratively insert these ranges, try to eliminate the variables in that sense. And if you can keep doing this until you don't have any more variables, then you have something that's can be statically determined if it's true or, yeah, well, if it's true. And if you can't eliminate all of the variables, then the result is not that you cannot show this, but simply that we don't know, in a sense. Okay, so to give you a sense of why this is Fourier-Motzkin-like and not just Fourier-Motzkin, basically we have to extend such an algorithm with rewriting of sums, but also for using array properties that we might have already proven. So the first step you could do here is to subtract the left-hand side from the right-hand side, and then you get a sum from I plus 1 to I2. And then you can split a sum like this. So now we are just splitting out the term that's I2, and then you have a sum from I plus 1 to I2 minus 1. But we already knew that this, from the range environment, can be eliminated to 1, and then we have 0 less than 1 plus some sum. But we know that from the blue range environment that this is a positive, always positive term, which means there's monotonicity in this. So that's to give an idea of the kinds of things you have to handle in this solver in order to prove these properties. Okay, and then from here you can use array properties further on in the program to derive other index functions, and in the end you could also use it to verify, optimize the program, which is our goal. So that's mainly what I wanted to say. I think I have like 1 or 2 minutes more. So maybe I wanted to show you our prototype. So what I showed you today is sort of a very simple program. This one, in fact. So if you run our prototype in the compiler, oh, we don't get the end. There you go. Then you can sort of, this is in a different notation, but you can see the index function that we've derived in the slides. But you can also see all of the intermediate index functions. So as a user, you might want to see these index functions, and then you can see them for each statement in your program. So it's like there's a one-to-one mapping between the index number, or like the names here and the names in your program. So this is, of course, a simple example for partitioning indices, but let's say you have an irregular array that is flattened, and you want to partition segments of indices. Then it gets a bit more hairy, and this is just to show you that this does get less pretty, but it's sort of doable. So we get an index function with 4 cases in this case, and you could imagine the complexity gets greater or worse from here. But this is our prototype so far. That's all I wanted to say. Thank you for listening.
Questions?
You said you are motivated partly by being able to do better optimizations. I was curious, like, what is an optimization that is possible with these proofs?
So one of the examples I had was if you're scattering, sometimes you scatter into a destination that's much larger than the values that you're writing. Sometimes you're scattering into an array that's actually smaller than the values that you're writing. But if you know that you're overwriting all of the values in the destination, you could not initialize that destination, for example.
Thank you for the talk. I had a question about the choice of modeling those algebraic properties with sums of products and some other things thrown in, I suppose, as well. So is this choice, well, maybe I'm just ignorant of this, but is this choice motivated? Is this like a model that people have used before? Because it also, the way you described it, did you roll your own solver, or is this like a solver that already exists?
So the solver is actually one that we're writing. Robert is writing it. But it's very naive in a sense. So we only have these ranges, and we need to do a lot of sort of partial evaluation in a sense. I don't know if that's the right word, but we need to simplify these statements a lot. And that's possible when you have such a restricted representation. It's much easier to normalize it when you are restricted to these sums of products. And I think that's a key thing that we are relying on in order to actually be able to prove anything in practice.
Okay, that makes sense. Thanks.
So for your example, you're trying to show that there are no duplicates. Would it make sense, instead of just saying giving the user the feedback, I don't know, then you can try to prove that there is a duplicate, and then you get particular evidence?
That's a good question. Yeah, because the way that we use the solver is that either we get a yes answer, this is true, or we get an I don't know answer. So definitely you could turn it around and then try the other direction as well. That's a good point. And actually, I also do this in simplifying some of these cases. So I will, for example, like I might not be able to prove that something is always true, but maybe sometimes I can prove that it's always false in a sense. So I try this in the simplification.
Can you go to the slide right before you generate the queries?
This one?
The one with a code.
This one?
Yes. So in the let t flags line, you're applying a function to this CS variable.
Yes.
Is it possible to just remove the CS variable and let the t flags be a function? Then that way the second line t indices would also be a function instead of a variable of an array. Then just delay all the function application until delay all the function on variables until the last line. So the rest of your so everything below it are just the functions instead of arrays. I'm
not entirely sure that I understand. In a sense, the C's is already an argument to this function.
But the C's is the CS is not a function, right? It's a Boolean.
It's a Boolean array.
Right. Right. So, but in terms of evaluation, right, you can just have everything just define a bunch of functions at the start, then compose them at the end when you apply it to your actual array.
Yeah.
So would that idea also work in this case if you structure your program like this?
So if I get what you're saying, it's sort of, so if you took all of these, I think it would be much the same actually, because here it doesn't have to be an array. It could be an expression, like you could write map. Maybe this is what you're asking. You could write map here, so you have an expression here. And the way that it's done then is that just you create the index function for this first, and then instead of having an intermediate variable for this in the environment, you just substitute it in here immediately.
Yes.
So yes, that works.
And can you write this whole let expression as a one-liner?
Is it one-liner? Yeah, sure you can.
Great.
I think so, at least.
Any more questions?
Yeah, thank you for this talk. This kind of cuts close to somewhat some of the things I'm interested in, just on my side playing around with things. I'm curious if you can productively produce proofs. It seems like, so if I understand correctly, you would need to declare, with the current system, you have to declare what kind of constraints that you want, and then you prove whether it holds or not. Would you, is it on your radar at all to have sort of some kind of tactic system where you could have some properties produced and inferred from just previously designated properties on the system? So like you could say,
so
without declaring that it's going to be a permutation, but some of the sub expressions that you're using force it to be a permutation, you'd be able to just infer it directly. And then the programmer could see, oh, look, this is going to be a permutation or something, maybe use that information
I mean, is a possible route. I think we're too early to care about stuff like that at this point. But for example, one thing that we care deeply about is inferring these index functions. And the index functions have a lot of information, for example, such as that. So maybe it could be a thing.
Thank you very much.
Yeah.
Right. Our next presentation is by Julian from the University of Aalborg, who will be talking about how to interpret the kind of data parallel array programming paradigm in another theoretical model.
Yep. I haven't tried these mics before. Is this correct? Yes. Can you hear me now? So yeah, I come here with my study group. We made our master thesis about this project and are going to present it here. So my name is Julian, and my group mates Chris and Lars are sitting in the crowd. And our supervisor could sadly not come, but he has also helped a lot. To give some context, in the last many years we have seen a very large growth of this GPU hardware, and yeah, we're at an array programming conference, so that makes sense. We're going to talk about that. We take kind of basis in this FUFAC language, which you have already heard about 3 times now. But we kind of abstract many of the things away, so we are not really looking at FUFAC. We instead try to look at like a general data parallel language and how this maps to other models for parallelism, such as process calculi, or more specifically the pi calculus. This might provide some useful insights into FUFAC programs. Although we don't look at that in this presentation, we instead look at how such a translation would look. So just a quick context, a quick introduction. The pi calculus is a process calculi, so computation are expressed through communication instead of through application of functions. So for example, we have here we can send from some process, can send on A, marked in blue, and we say sending by having this line over, and then we can parallelly compose that with another process marked in red, which can then receive that message. And the pi calculus which we are looking at is more special than other process calculi in that it allows for name passing, so we can send the name B on this channel instead of just sending an empty message. And this B can then be used for further communication because it can just be used as a new channel. This allows for pretty complex programs to be made. So we can see that it transitions into the process P, which is like a sub-process, and this process P is now unguarded and can be run itself, and we apply the substitution which comes from the communication. I have to make sure of time. These process calculi also allow for arbitrary parallelism through this unbounded replication, which we use the exclamation mark for, and that's just expanded indefinitely. So another quick example, we can create private names. So in process A1, we create a name B, and we can send that on channel A, and then in another process, we can send A itself on channel A, and then we can receive that A and then send the number 3 many times, as many as we want. And we can see that this reduces or transitions in 2 ways. It can either be process A1 that sends or A2. So it's kind of undeterministic, and we don't know what we end up with until we see what happens. There's been a lot of work on this calculus by Milner, and we base our work on the tutorial he wrote in '93. There's also been previous work on translations on the lambda calculus to the pi calculus by Milner also. And we also take a lot of notation and the proof technique from Amadio in their translation. Just to quick, doing our project, we had some problems. It was kind of hard creating these parallel structures and then also proving them to say that our translation was correct, because they kind of exploded with many possibilities in what could happen. We also found it hard to create a cost model of the pi calculus to compare performance with FUFAC, like how would performance increase by doing the translation? That was kind of hard to say. Quick context, you already had this before, but FUFAC is this pretty interesting purely functional array language, and where you can kind of write parallel programs by using operators known from functional languages. But we are not interested in many of the things of FUFAC, so we create a simpler version which we can, well, it's called basic untyped FUFAC, but it's just a lambda calculus with arrays. So we can have these arrays, and then we can use second order array operators on them, actually only map, because we had to keep the scope down. And we also do tuples to do stuff like applying multiple parameters to functions. Yes. So the syntax is very close to the lambda calculus, and we basically only have these built-ins, which are like operations on arrays and numbers and arithmetic, but we also allow kitting arrays. That makes sense. It's a call by value lambda calculus, so yeah, that's going to become important in the translation. Arrays, they are evaluated in parallel, so we can, or not in parallel, but we can say that it doesn't matter which element you actually evaluate in arrays. For the pi calculus, we have seen it a bit, I told you about it before, but we have these chains of actions which can either be sending or receiving, and they can these chains can then be composed, parallelly composed together. And then we have these two kinds of name bindings, either receiving, where we bind to a name, or where we create a new name. So the semantics is built up in two parts. We either have this structural congruence, which is like a syntactical rewriter, where we allow to rewrite, for example, the new name. We can create this, move the scope of a name in and out, and we can have this replication where we just keep unpacking a new process from a replication. For example, we can send an A indefinitely many times, as I told before, and then we have these transition rules for communication and for allowing the usage of the structural congruence. And this creates a rather simple semantics for this model. To close the gap between the two languages, so the basic untyped FUFAC and the pi calculus, we extend the pi calculus with a couple of extensions, such as we allow to send numbers and arithmetic through the applied pi calculus. And then we also allow for broadcasting. Instead of just having point-to-point traffic, we allow for one sender and many receivers. We use this colon for that. And that is inspired by Ene and also Hans. And then we also allow to compose channels and then some static number or label, basically creating a sort of indexing in the pi calculus, and that is inspired by the polyadic synchronization of Carbone. So with the gap closer, like we can start creating the translation. And as I said, that has been inspired by previous work, and all you see on this slide is previous work. Where the translation basically depends on an expression and an output channel. So basic untyped FUFAC expression, and then an output channel for where the result of the computation should be returned on, because the processes cannot themselves return results. They have to return it via some channel, so we have to facilitate that. And we use the following notation for that, these square brackets, and to show some basic examples, we can create functions, and we can do translate simple single values, and we can see that if we have an x, we just return that x on the output channel. If we have a function, we create a new name f, and we return that f on the output channel, and then this f basically becomes a handle for an always available server, which is ready to take requests from if I want to call the function. So it's not application, but communication. we will call these handles and also later use the name handle for arrays. But I will only talk about arrays and not the other parts of the translation, just to keep it short. So how can we express arrays? We could maybe say that we just send each element on a channel O in parallel and just include an index to give some order. This would allow for like a map-like structure where we just listen on all the elements on O and then do something with them, could be the P. Yeah, could do something with each element. This is not that smart because we can not do indexing, and once we have read the array once, it will be gone. So we use a couple of these extensions to see what can be done about that. We create these persistent cell structures where we can, which facilitate two things. So marked in red, there is the cell structure, where a single cell serves a single element, where we can either listen on the name or the handle of the array composed by an index for indexing, or composed by this all label, such that we can get all the elements out at once. So for an array, we would create this cell 3 times, and then return the handle on the O. Just like abstraction, we have these O's which return values, and then the values are either like 1 and 2 and 3, or some handle to a server somewhere. So to do a map, it's we can just create an array as shown in red, which we call h1 for a substitution, and then we can create a new name A and send that to the array, and the array will then return all its values on A. Then we can, for example, create a new cell for each of those elements where the value is now the value +1. For the actual translation, we would need to actually call the function f, like communicate with the function f, wait for the result to return, and then put that into the new cell. So I talked about how basic untyped foo-faq we created. We said that it was called by value, and that kind of turned out to be a bit of a pain, because in the previous example, when we create this new array, we have to make sure we don't use it until it has been fully evaluated. And also that we don't return it on the O channel before the sub-expressions are evaluated. So we kind of create this wait statement where we say that for each cell we create, we receive on a channel C, and then we have this process called repeat, which will repeatedly send a signal on C some X number of times, in this case 3. And when it's done sending those 3 messages, it will send a message on done, and then after we receive on done, we can return on O, basically to make sure that the evaluation strategies match between basic untyped foo-faq and the translation. Because the way we prove that the translation is correct is by taking each step, like we say a single step in basic untyped foo-faq, must be matched by a couple of steps in the translation. And to keep track of this, we mark the PyCalculus transitions as either important or administrative. Then we can say that we say that, I'll come to that later, but when we can mark the translation through this static annotation and say that we cannot pass a dot without taking an important transition. And that way we can kind of, the administrative transitions kind of become a sort of facilitation for the translation. So all the moving around of values like O channels and stuff like that, those are unimportant and administrative, but the important is like calling a function and stuff like that. And we use this for the proof because we want to collect all the we want to collect all the processes which serve a single step of basic untyped foo-faq together. And we do this by a bisimulation, where we say that if a process P and Q only differ by administrative translations. They are the same, kind of. But if one of them can take an important, then the other must also take an important. And that way, one cannot run ahead of a bullet without the other one having to do the same. Then we also went into the problem that we have numbers. So we got two processes, P and Q, which return the same result, or not the same result, but they do the same and return 5 and 6. So we also want to make sure that they can be differentiated by an arbitrary context. We use this to create an operational correspondence where we relate basic untyped foo-fak expressions with these processes, such that when the basic untyped foo-fak expression takes a reduction, then our translation takes an important transition, and vice versa. And then we create a relation R, which is all the expressions and their matching translation. And then if by showing that that is the operational correspondence, we know that the translation is correct in that transitions in the translation match the translated program and vice versa. So we do believe that it is correct. And just to conclude, maybe I talked a bit too fast, but it's fine. Yeah. We conclude by saying that we have created these two languages, and they basically close the gap between data parallel languages like foo-fak with models like the PyCalculus, and we propose a translation, and we also show that this translation is correct. However, we did have a lot of issues proving this translation, and we often had that the transitions it could take kind of exploded if we didn't keep track of or didn't limit it, for example, with the repeat process. So yeah, for future work, it would be very interesting to look at other evaluation strategies. That's the last point. Because what if we could emulate, for example, lazy evaluation? We could let, so these cells, we could maybe let a cell like run way ahead, like maybe multiple maps ahead, while other cells were not used and they just went they didn't go ahead and stuff. So maybe this PyCalculus fits better with lazy evaluation. That would be interesting to look at. Also, the translation is only looking at these untyped languages, and there exist a lot of really cool type systems called sorts for the PyCalculus, and they would be interesting to look at. What would they mean for if we translated concepts from maybe foo-fak or other data parallel languages? Would they fit some of the sort systems for the PyCalculus? Then we were also not very glad that we used these extensions, and would be interesting to look at whether these were necessary and whether they are fair, and what would it be the cost of omitting them. And lastly, the operational correspondence we created checks whether they match each other, but it doesn't check if the translation just goes off into a tangent, just evaluating administrative transitions forever. So that is definitely a future work. So thanks to the foo-fak project for talking with us and helping with us with our master thesis, and yeah, the nice people at DICU. Yeah, I think that's it.
Thank you. This was quite interesting. Simple question about, you have the repeat function there. That's like a basic concurrency latch. Did you investigate any other kind of concurrency primitives for synchronization?
No, we actually didn't, and we kind of created it as a sort of, oh no, things are going wrong. We need this kind of synchronization thing to ensure that not only that we emulate call by value, but also that we have all the cells ready for when we send a broadcast to it.
I mean, in this case, yeah, it seems like kind of a hack.
Yeah.
But I mean, in general, for this PyCalculus, you would for more complicated semantics, you would need some sort of
Yeah.
synchronization primitives. And it seems like you started going that direction.
Yeah, so yeah, I didn't know about that. That's pretty interesting, and it's definitely a future work to look at how that would incorporate in the translation, because it's so parallel, you would need to put some bounds on it.
Okay.
Yeah.
Thank you very much.
Hmm?
Other questions?
I didn't get a sense for how much of the translation spend is dedicated to your administrative side versus the dark bullets, I guess. Do you have a feeling for what the overall ratios are?
A lot. There are quite a lot of communication happening to return values from sub-expressions. For example, if you create an array, you would need multiple communications for each of those sub-expressions to evaluate and return the result, and you can just the returning of an expression requires one communication that's administrative. So I would say quite a lot.
Maybe can I ask a very high-level question? So, PyCalculus is about communicating processes, right? And you made the translation from an array language, which is basically lambda calculus with all the properties that we know and love, and into something more kind of processy. So, what would be a good application of this model? So, I mean, could you handle something like, I don't know, distributed systems, or so do you have some realistic application in mind, or it's just a theoretical exercise?
Well, you save distributed systems, and that was what we talked about a lot in the beginning, because that's pretty interesting that you could maybe say that like a part of the program runs in this place and at this place, but we found it hard to like say when do you stop with the PyCalculus and when do you go back to sequentially doing stuff. And I think like it's not a very realistic model that you have parallelism that goes so deep, like and it's hard to then map it back to some sequential afterwards. I would say I think it's interesting to maybe look at those analysis and all the work that has been done on the PyCalculus and maybe applying that to data parallel languages, which has been translated maybe, but that's not something we looked at.
Maybe some mix of PyCalculus and lambda calculus, or PyCalculus
Yeah, exactly.
to parallelize and lambda calculus
And
to
that actually exists. The one of the derivative or one of the works we had from Amadio created this concurrent lambda calculus, which is basically a combination. Yeah, that would be interesting to look at.
Have you looked at Erlang or Gleam much?
No, sorry. I want to, but I haven't looked at them.
Okay, I was just going to suggest that might be it. I mean,
Yeah.
this is like right up in their alley, so.
Yeah, and a lot of programming languages, I don't know the original one, but I wrote Go, and the whole concept of these channels is very similar to that.
Right. I think like the sort of primitive concepts where everything is a process would be right on the Gleam. And so if you talk to some of their guys, they would have probably a lot of, there might be some previous literature that you could.
Thank you. Yeah, I will do that.
If there's no more questions, let's thank the speaker again. And, I think this is the end of the first session, so yeah, let's meet after lunch. Can I ask the speakers of the second session to try their laptops so that it all goes smoothly? All right, thanks for coming after lunch. I see the full room, so it's good. No, we didn't lose a lot of people. So this session is called Performance, even though it's a bit of a made-up name. And the first speaker is Vanessa, who's going to talk about Apple array allocation. So please go ahead.
Okay, so to start out, I'm going to talk about compiler as a library, a sort of new hopeful architecture for compilers, talk about the actual technical details for static memory management, no garbage collector, there's also no ownership the way Rust has, so hopefully easier on the programmer, and demonstrate some polyglot workflows. So a little bit showing off what we can do with Python alongside our array programming. There are three sort of inspirations. The first is that array languages suffer from a lack of embeddability. The idea here is rather than competing with NumPy directly, we turn to C. You may have read Kell's polemic on C. One of the things that C does well is you can embed it. People frequently call C libraries. You can compile C libraries to C procedures and so on. Also much easier for the programmer. You can use established libraries. For the array programmer, you can use established libraries. You don't end up being deprived for using this arcane language. It's a high-level language, but also informed by the backend, which I think is sort of not as familiar to Haskell side of things, right? So we ban certain things in order to get better performance, easier implementation, which, in Haskell world, if you say arrays of functions are banned, there's no type theoretic reason. I do think the sort of APL array side of things are sympathetic to this approach. And it's also a nice example of how you can do sort of whole pipeline compiler design, a nice trick for static memory management. And as it turns out, array languages are a good candidate for sort of new compiler architectures. In some ways, they're simple. You can do a lot of non-trivial stuff and beautiful stuff without relying on too much of other people's code. So rather than having a compiler which you call on a file to produce an object file, you could have a compiler which is a function which takes a string of source code and produces machine code. It'd be really nice if you could have another compiler call your compiler or just call out, right? So you'd be able to write procedures in the same source file because it's just a library function call. You'd be able to run code from your editor. You could send code across a network, and it'd be a few hundred bytes, no RTS, no garbage collector that you need to deal with. Here's the, completely flat arrays. This, you only need one allocation here. So it just stores the rank, then it stores the dimensions, and then it stores the elements. There's no arrays of functions, there's no arrays of tuples of arrays, and there's no recursive data types. No lists are allowed in this language. So everything is completely flat, one allocation and one call to free. The language itself, just a demonstration, callback library divergence to show you can do non-trivial stuff. It's functional, expression-oriented, immutable. There's no recursion, and all looping is implicit, which will turn out to be important, but you can still do interesting things. Okay, so this is the compiler pipeline, very typical in many ways, straight from the compiler implementation in ML textbook. Basically, we generate the IR, which is a series of statements. We do liveness analysis to find out when arrays are live during the program, and then we insert free statements into it. That way we don't leak memory, and we don't need to worry about, manual stuff like double free. This is the actual array. This is written in Haskell. This is pretty typical, I think. So there's expressions, and there's statements. The statements used to read or write memory. It's close to assembly. There's jumps. And basically what we're going to try to do is try to treat arrays somewhat like registers. Compilers use liveness analysis on registers, which is not entirely possible. But if we do a little extra lifting on the compiler side, it ends up working out. So, so this is, right, this is the iterative liveness analysis, very typical. This is just for registers. You construct a control flow graph with your statements. Then with the annotated nodes, you can figure this out. The trick here is these aren't registers, these are arrays. However, because it's a high-level language, we can label them all. Within the compiler, we give a unique label to the array. And then from that, we'll be able to do, every statement we see which arrays it defines, which arrays it uses, and we can compute from there. This allows pointer aliasing, so we can access the data from one register and access the rank or the dimension from another. Because it's a unique label, because the label is internal to the compiler, we still get to treat it as the same, and we won't have any problems with, we won't have any problems tracking liveness. Oh, and there's no references. Because there's no references, no array can keep another array alive, so that keeps it straightforward. There is one big subtlety, which is that the frees must be reachable. So with registers, all you care about is where they're live. Here, we don't want to leak memory, which means we also have to worry about the control flow graph. So it's not enough to just say, well, it falls out of liveness here. We also have to make sure that the free statement is at a reachable part. It turns out if you make the loops jump backwards, this basically falls out, and this is more efficient on processors by convention. So if we try the sort of fraught, difficult way, we end up with the live, or the free being inserted where the live interval ends, but it's unreachable, which isn't good. If we make the loop go backwards, then the free is reachable. It occurs as soon as the array goes out of scope. So this actually turns out to work. The IR is generated by us. There's only a few cases. We have one function to write loops. There's only one way to write loops. There's also conditionals, which turn out to work. And we also have to avoid loops that do nothing. So empty folds are a type error, for instance. That's not a problem. We have to check for like mapping over. But in this case, by careful management, we do get something which is memory safe, won't leak memory. Here's an example just to show that it does work. We can const one onto some generated array, and the compiler will, since it's immutable and copying, the array that's generated gets freed before the procedure returns. This is also fun. You can dump the intermediate representation inside the just-in-time compiler, inside a REPL, which I think is good for my debugging and also just a fun feature. And just to show off some of the advantages of this sort of compiler as a library embedded procedure, here's matplotlib. What I'm doing there is I have a program to generate numbers sampled from Gaussian distribution, as you can imagine, randomness is hard to debug. So we go to matplotlib, and with a histogram, we can sort of guess, okay, this is in fact normal, a normal distribution, and this is correct code. You don't have to implement all of the existing established libraries in order to benefit from them. And you can write the code, which is more laconic, more fun, hopefully. This is, Bessel functions of the first kind. This is in a Jupyter notebook with R and ggplot. So the Apple code I don't think is the most elegant, but at the same time, you do see you can do non-trivial things within the language, even without explicit loops, even just with arrays of numbers. You can also read CSVs without, you read CSVs in Python, rely on something else. The idea here is, well, maybe array languages aren't the best for parsing, that's okay. As long as it's comfortable and fluent, we can still, or comfortable and fluent to do these sort of polyglot things, we can still have some of the advantage. This calculates inflation percentages. So we have one little, I think this is dyadic infix in J with a map, and all of the CSV processing, column selection is done in another language. Here is the 120 lines of R code for the just-in-time compiler. So it is, not perfect, but it's reasonably easy to add bindings to another language. The Python extension module is, I think, around 200 lines of C, so also not so bad. One of the things C does well, for instance, is the canonical implementation. If you write zlib, Rust has bindings to zlib, Haskell has bindings to zlib, and so everyone benefits even if you don't write C. Here, we'd like to have a canonical implementation. This is the shoelace theorem. You can compute the area of a polygon from its coordinates in Python and in R. So pretty much you write the same thing, you write it correctly, you write it once, and then you distribute to everyone to benefit, hopefully. You can also compile the same Apple code to an object file, call it from C. This is just to show there's no need for a runtime, there's no need to interface with a garbage collector. This is, it's pretty lightweight, it makes few demands of its host environment. Because it makes few demands of its host environment, the hope is it becomes, more widely used. In terms of exporting and making array languages plausible for other environments, you want to export the ability to debug. You want to export things like, J has forks and trains, but you can't use them in a foreign language. The only thing you can export is, procedures, for instance. So that's a difficult question, but you do want to be able to export your debug facilities, so you can print the, inspect the type. You can dump the assembly, and within Python, just to see, for instance, that loop fusion occurs. There's a no SIMD, but basically this gets, you can debug things. Oh, thanks. Whoop. Okay, future work. I do think this is promising. I have not implemented this, but consolidating allocations, right? So if you have two ranges, you're concatenating them, and the second range is smaller than the first. So the output, you can allocate the output, you can allocate the first, and then when you're done reading from the first thing that you're concatenating, you could put the second argument into the space that the first one used. There's shape types. So since we know that iRange 091 has size 10. iron 4.1 has size 5. In theory, we could put the second argument into the slot that the first one has, which hopefully would get on par with at least like reference counting in APL. I'm not sure anyone does this, but I do think there's performance boosts from static memory analysis. Okay. Questions? Oh, the future, yes. Okay. Oh. Oh, there we go. Oh no. Okay. Yeah. 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 Yes, or that's a different optimization. That's a better optimization. This is, I guess, a small example, but I think the idea is here, if you have arrays allocated over the course of the program and you know their sizes, then you should be able to like fill in the blank spaces using some of this liveness analysis. Liveness analysis methods, yeah. Yeah, yeah. For the, yeah. Well, so you allocate the output. That has to happen. Then you allocate the left-hand side. Well, this is in this example. And then, you know, once you've gotten to concatenating the right-hand side, generating the right-hand side, you can reuse what you allocated for the left-hand side. I think maybe this example is too simple-minded, but basically the idea is, yes, there are programs where if you know the size via shape types and you know the liveness information, you could be able to do better allocations.
Yeah, let's assume you would. Sorry. I think the better example for what I now understand what you want to show would be something like A plus B goes to C, where you have A and B and they all have the same shape or size, and then you could store the result in one of the arguments.
Yeah, yeah.
I think that would be, but that's what many languages would do.
Yeah.
Okay. Okay, thank you.
Yeah, so do you have an idea of where you would position the power, expressivity, and so forth of this allocation with things like region-based memory allocators and stack-based systems and ref counting versus garbage? Like, in the whole space, where do you feel like this falls?
So I think it's a little, well, it's a little easier than Rust, I'd say. So compared to, I guess, like ownership, and then compared to garbage collection. I think the advantage compared to garbage collection is mainly you don't have to link in a big RTS. Compared to reference counting, I do think APL does good stuff there.
So if I understand correctly, I might be wrong. You are doing a sort of register allocation on arrays?
What notation? Or,
a sort of register allocation like technique for arrays, right? So how tuned is this procedure? Like, for example, you know, because I could have a big buffer, and then the next thing that I could reuse, it's a very small buffer, but this will occupy the big buffer. Are you chunking also the big buffer? Are you segmented it? Or you are just, even if the buffer that is necessarily for the reuse is very small, you are going to consume the whole buffer that is potentially very large? Or are you trying to figure out the best, the size that fits best, or how?
Well, I mean, if you have like a slot of memory from an array that's like 1,000 elements, and then you have subsequently you use part of that for something with 2 elements. If you know both of those sizes from the shape types ahead of time, you could just say, okay, and well now I have 98 over here, right? So I do think, yeah, that would be promising.
Okay, thank you.
So how fragile or composable and scalable do you think this technique is? Like, are you going to hit hard limits as you try to expand the language features, do you think, pretty quickly? Or is there a path towards either composing it with other types of technologies, or do you think you can continue to grow this to more sophisticated languages with less limitations?
I think some things can be worked around, like maybe it might be possible to do like closures, arrays of functions. I think with like if you had arrays of lists, that wouldn't be possible. I think what I was trying to do here is you have an array, like a core array language, and then you offload the other stuff like linked lists to the host environment. So the hope is that this is not much of a limitation. You could add like algebraic data types. The main thing is no references of references, which I think that would be a hard limit probably.
Great. So the JIT compiler itself,
Yeah.
so that's written in C, or?
So that's written in Haskell, yeah.
Okay.
Yeah.
So, okay.
Yeah.
This might be a very naive question. I don't really know what the ABI for like something like APL looks like, but why would I prefer this as opposed to just like writing some APL and like compiling it to something that I can then call into from OCaml or whatever?
Well, I do think you could probably have a similar compiler architecture for something like APL. I think the preferable part is, if you have a compiler as a library, there's a lot more you can do, right? So like if you have 2 languages in the same file and you can inspect the types in both languages in your IDE, that's much more convenient than what's typical now, which is like you have your Futhark code, which you compile to Python. So if you've already, Whoop. Yeah.
Maybe following up just we have a few more minutes. Maybe following up what Aaron was saying. So it seems that your technique very much relies on the ability to do this liveness analysis. Therefore, you have to do a lot of, well, maybe not a lot of, but quite some significant restrictions, right? So you don't have recursion, right? You don't have. I'm not sure what's the looping situation is, and so forth. So I mean, what I'm thinking is. How do you feel at least? Do these restrictions stop you from writing interesting algorithms, or you think it's always the possibility to overcome this? So what's the kind of relationship between the restrictions and the code that you can express?
Well, so I didn't do recursion or like explicit while loops because you have to be careful with the looping. I do think you could add more looping facilities, maybe even recursion. I'm not 100% sure. But in any case, I mean, you can write non-trivial programs, and the hope is if it's fluent enough, then you won't care and you'll write the rest in your general purpose language.
Okay. Thanks very much. Let's thank the speaker. So the next talk is given by Thomas, and it's about Shrey. Thomas, go ahead.
Thank you. So, is this here? Okay. Before I want to talk about what Shrey is exactly, I would like to motivate why we need Shrey. So, when doing scientific computations like solving differential equations, that kind of stuff, these are often very fast algorithms like linear or n log n. And before the time runs out, you're probably going to run into an issue where you just do not have the memory in order to make your computation precise enough. So I've done a few numbers on the machine we have at Radboud, just to give you an idea about the kind of time you have. So if you fill up this 128 gigabyte machine to its entirety and do a full multi-grid method, which is for PDEs, it takes less than a minute. And even for Fourier transforms, it's a few minutes. And you may have a number of these primitives in your simulation, but still, if you start the simulation when you go home, then the next day you will have your results. So there's a limit to the amount of memory we can put in a single computer. So the way people solve this is by taking a bunch of computers and then connecting them to a network so that they can pull together both their computing resources as well as the memory. This is pretty hard to program because you have to take care of data placement explicitly, of communication explicitly. So kind of the dream is that we have some kind of array language that is close to the math, and then the compiler will take care of creating an efficient distributed program for you. So the semantic gap is obviously very big here. So what Shrey aims to do is to sit between this and kind of abstract over the distributed memory. So Shrey is a form of DSM, of distributed shared memory, which means that it imitates shared memory over a distributed system. But instead of doing this for the entire computer, like in classical DSM systems, it does it only for specific arrays. So when you allocate a piece of memory, you can say whether you want this to be replicated on each node or whether you want this to be distributed. And there's also a owner compute restriction, which means that we have a concept of ownerships. I will go into detail later. And only that node is allowed to write to it. And that allows for a efficient and simple implementation. And I will argue that that is good enough for numerical codes that these kind of array languages target. Well, I think at the open mic I already told this a little bit, but the implementation is pretty rudimentary at the moment, so I will focus in this talk on the main design ideas and not the exact implementation. So I want to introduce a motivating example to kind of give you an idea on the kind of problems we solve. So there are iterative methods that consist out of multiplying a matrix with a vector repeatedly. And often these matrices have a lot of zeros, which means that it would be a ways to store these and multiply by these zeros explicitly. So a matrix with a lot of zeros is called a sparse matrix, and you have an example here. So the color thingies are non-zeros, and the rest is all zero. And we store this as three arrays. We have the values in just a linear one-dimensional array, the corresponding column indices. And then we also need to know which values belong to a row. Because if you compute a matrix vector product, then you take one row of this matrix and take the dot product with a vector. So that is why we have this row boundary array over there that shows the first and the last element of each row. So in SAC, which is an array language, it looks something like this. And then for a single node, it's not hard to generate the code. It's pretty straightforward. Your map thing becomes a loop, so that's the outer loop you see there. You can parallelize this. And then we have an inner loop that sums up the values, which is the reduction, the sum in the middle. However, for distributed computing, this becomes a lot more difficult because we need to know where the data is stored, and we need to have some kind of correspondence between the global data structure we know exists and what actually is in the memory. So if we would like to generate explicit MPI code, then we would have to first conceptually divide the array into pieces. So say we have 3 nodes, then we'd say, okay, conceptually we have something like this, and each node is responsible for computing one of these 3 parts. And then in the actual code, each node just has one smaller array and an identifier, which is like 0, 1, 2, etc., that says which node it is. And we can then make a correspondence between our local indices of this thing and the global indices of the entire array. So in this case, you would multiply your identifier by the number of elements in one of these blocks and then add your local index in order to get the global index. So that means that we would get something ugly like this code. The outer loop is still fine, it just loops over a restricted range. But on the inside, we have to compute for every axis on which node the data lives and what the local axis is, local index is. So then we get, for example, this local check, and if it's not, then we have to compute nodes, call MPI on it, and then sum the array. So this is both quite ugly and quite expensive because we have all of these explicit MPI calls in the inner loop. So we decided to not do this. So the main problem with DSM is that you have to take care of memory coherency. So if there are multiple, if your data exists in multiple places, you need to know who has the valid copy. And like we just saw, the reading is difficult, but the writing is not. Like if you define functions or vectors, you usually define them pointwise. You say f I comma j is equal to something. So we have control over the writes, but not the reads. So we just say, okay, if you have the element on your node, then you're the only one who's allowed to write to it, and that makes the memory coherency trivial, because the node with the valid copy is the one that owns it. So instead of having one local data structure, in Shrey we just allocate the entire thing in virtual memory and make sure that only part of this actually exists in physical memory. So if you're node 0, then there are 2 helper functions, Shrey start and Shrey end, that tell you what part of the array belongs to you. And depending on which node you are, you get different pointers here. So that way you can keep track of what you need to compute. And that means that for parallelizing this code, you don't have to touch the inside of the loop. The only thing you need to do is you have to tell Shrey that you want to parallelize, that you want to distribute your array. So that is this Shrey malloc thing. The first element is the size, the first argument is the size of the first dimension. So in this case it's just n, but if we have an m by n matrix, you may choose m there. And then we restrict the range to Shrey start and Shrey end. And then if we want to use this array after, we need to make sure that all nodes have finished computing before we start reading. So that is why there's this Shrey sync function that is more or less a barrier synchronization. So there are things you can do to optimize this MPI version I showed you first by doing some static analysis, but this is pretty brittle. So we have done some benchmarks. Here I've presented the results for 3 languages. UPC and Chapel take kind of the MPI explicit approach by inserting communication primitives. And Shrey does this all at runtime. This is a conjugate gradient method which uses the sparse matrix vector multiplication of the example as main computational kernel. And you can see that as soon as we go out of node, so between the 1 and the 2 we use 2 physical machines, that we get a huge drop in performance. Also for Shrey, because this is a very small example, but you can see this logarithmic scale, so there's like a factor 100 between it. So explicit communication can work well because you have less overheads, but it's pretty brittle for performance. So on the technical side, the basic idea is that we rely on segfolds. So the grayed out part is part of the memory that you are not allowed to read or write to. And the black part is the memory that you own. And you do have full read-write access there. So you can just do your normal thing. You can pass this memory to an external library if you so wish. And as soon as we hit, for example, this data access at node 0, then this will raise a segfold. And we can catch that and make sure that we communicate the data from the correct node to that position. This works in a cache manner, like a cache, because we don't want to have too much physical memory at each node. So after a certain runtime configurable amount of memory has been used, then we unmap parts that we fetch from other nodes. So if we have to read that again, we would have to communicate this again as well. And yeah, there are some more technical stuff, but this is the main idea behind the implementation. So in order to make distributed programs perform well, we need to make sure that the synchronization is cheap, but that kind of trivially holds because of this owner compute rule. We need to minimize the amount of data communicated, but I feel like this is more a property of the algorithm rather than the actual Shrey library. For example, like a blocked matrix multiplication on CPU is made so that the data access is good and that you do not have to communicate too much between RAM and CPU caches. And that same idea will also hold for Shrey. And then finally, we have to mitigate the latency of fetching elements, and that is important to handle within Shrey. So we have basically two complementary strategies of dealing with this. So naively, your communication pattern might look something like this. So we segfold, then we have to do some Shrey overhead, like computing where do we get the data from. Then we have to wait for the data to arrive. That is all the red part. And only then does the data start coming in and we can do something with it. So that is the green thing. And you can see there's a lot of red, so there's a lot of overhead. So a simple thing, just like hardware caches solve with cache lines, is to not fetch one element at a time, but to fetch multiple elements at a time, so you can spread out this latency hit over more data. We have a runtime environment variable that you can set for this Shrey cache line. And for many applications like a matrix multiplication, a stencil, a blocked and body implementation, this is enough to reduce the latency to almost nothing, because you can fetch a megabyte at a time or even more. And because all of these algorithms are optimized for CPU caches, this carries over to Shrey. So we can profile the amount of data communicated. And for matrix multiplication, we see that it is actually the minimum amount that's only communicates like 3% more than a handwritten explicit communication version does. So this works fine in cases where we have good temporal and spatial locality. But for things like conjugate gradients, sparse matrix vector multiplication, your data accesses jump all over the place. So if you take a large contiguous block, then you're just communicating in a bunch of junk, and that unnecessarily stresses your bandwidth. And also it doesn't really help with the latency. So instead we encourage people to use multi-threading in their code. It is completely thread safe, Shrey. So they can segfold and communicate data at the same time. And that way we kind of overlap the latency penalty, because your T threads can segfold at the same time, and then they can fetch one page at a time. And that way we do not have to put in a bunch of junk. This never hurts, but we are limited by the number of threads. Like if you have 8 threads, then you can cut the latency by at most a factor of 8. So in some cases this may not be enough, but it seems to perform decently. So this is the same benchmark I showed in the first picture with the large performance drop, but on a much larger data set. On the right-hand side, we have the figures for Shrey. This uses the OpenMP version from the NASA benchmarks, and then I just threw in the Shrey malloc on the allocations and hit the loops. And the MPI version is also from NASA, but that does not use OpenMP, unfortunately. So that is why you see that at the start, Shrey is a bit faster. And here you can see that going from 1 to 2 nodes, we get some speed up. Afterwards, our speed goes down a little bit. That is because we have a very poor interconnect on this machine. It's just a 1 gigabit switch that all the nodes are hooked up on. So MPI is able to get better performance because it can, so conjugate gradient does a sparse matrix vector multiplication multiple times. So what you can do is you can analyze the communication pattern and communicate only exactly what you need on each call afterwards. And we can do that in Shrey, but we still get within a factor 2. And it is also scalable. So I think that is a very decent result there. So in conclusion, Shrey is helpful when you want to handle problems that are too large to fit into one physical machine. It's pretty easy to use. It acts just like OpenMP that you can watch for data parallel loops and then restrict the range. It should also be easy to integrate in compilers and other tool chains because it works with segfault, so it does not care if you call some external library on the memory. And if you want this too for your language, you can pull it from here, and I would also be interested in collaborating on that. So, are there any questions?
Questions? So I remember when I took HPC classes many years ago, that I was also taught about these ways of simulating shared memory across a cluster using virtual memory techniques. And then for reasons I don't remember, they said they didn't work very well. So can you compare the Shrey approach to whatever didn't work back then 15 years ago and what you do differently?
So I think the main difference is this owner compute rule. So say you have a distributed shared memory system like Samhita, then there are nodes that are responsible for handling the memory and nodes that are responsible for doing the computations. And that means that each node has to ask the memory server, I would like to compute this cache line, and then it computes a page, sends it back to the memory server, and this memory server is responsible for handling the coherency. And this is difficult to scale, and it has a lot of overhead. And for Shrey, we don't need to ask ourselves which node is responsible for what computation, because we just have a blockwise distribution of the array. So this is less flexible. Like you can't write a compiler or maybe some very irregular graph algorithm this way. So that is the trade-off you make. But for many algorithms, this is sufficient.
Well, thanks for the nice talk in the first place. I wonder, did you think about comparing it to the performance of the SEC cluster backend, which is based on the same ideas?
It does not currently run.
Too bad, yeah.
So we have to try this. The main difference between this and the SEC cluster backend is that that uses a explicit index transformation on every axis. So I would expect this to be faster by a constant factor, but have similar scaling behavior, because it does not need to check on every axis. The Shrey version, yes. And also, I believe it's not memory scalable because it allocates the full array in on every node. No, but actually physically. No? Okay, well. Okay, I would have to reread the paper then. But I mean, it is in a sense similar. But the main difference is that we have we don't need to change the data accesses when reading memory. Okay, maybe we can.
So when you get a segfault, you pull in some cache size block around that region. Is that right?
Yes.
Okay. So is there a way to get control over the batch size of how much? Is it just the cache line option to control how much you read from another space? Because I would imagine that is critical to optimizing some of these, is being able to prefetch data of a very specific size.
So it has to be a multiple of the system page size, which is 4069 bytes on most systems, because that is the granularity that the MMU works at. Other than that, you can take any multiple of this. At the moment, it is implemented with a global environment variable, but there's no reason you couldn't do this on an array basis. Is that? Yep.
I have a question.
Ah.
Okay, yeah. When you pull in the cache, how do you then save it? Because you don't keep the full array, do you then save it, allocate more space for that, or?
So we just set the memory protection to read only whenever we pull in an element. And then we can read and write to it. We don't have to copy it. And if we want to get rid of it, then we unmap it and remap it again. And the way Unix system works, because they allocate lazily, then it gets kind of kicked out of RAM.
Can the ownership is the ownership supported over a partitioning on block tiles? Like, let's say rectangular tiles. I would like to give this ownership to a.
So it is always one-dimensional. So you can, if you have a square, you cannot do it like this.
Okay, so you cannot block it.
Well, you cannot do this if you view the array as a 2D row major thing. So instead, what you would do is you would view it as a 3-dimensional or 4-dimensional array of the smaller block pieces, so that the linearization looks something like, you know, the Morton order thing, and then you can do it, but it requires a little bit of work. So I think.
And overhead, because you have to. I imagine it resides somewhere, so this would be a whole operation that you have to do all over the cluster, and it's kind of a.
No,
you will have to communicate, right?
No, it's more of a conceptual difference. Like, you store your data as a higher dimensional array. So in memory, it looks the same as for MPI. It's still just contiguous in memory. It's just that your indexing looks different. So depending on the exact benchmark and if the array language can optimize your array access a way that may give some overhead, but no communication things.
I guess, yeah, thanks very much. Let's thank the speaker again, please. I think so. The next talk is by Ivo, and we'll learn something about combination of task parallelism and data parallelism. Please go ahead.
Yes, thank you. So I'm Ivo, and I'll talk about how you can combine task parallelism and data parallelism with our new work assisting scheduler. So first of all, let's see if the slides work. Where's my mouse? Yes. So first of all, what is data parallelism and what is task parallelism? So first, data parallelism means that we in parallel execute the same value or same operation on different values, and this is also known as loop parallelism, where we execute the same operation on different iterations of a loop. And the other form of parallelism is task parallelism, where we in parallel execute possibly different operations. And you may also know this as control or functional parallelism. If you then look at array languages, then you could view data parallelism as the parallelism within array operation and task parallelism as the parallelism between different array operations. And the parallelism within an array operation is usually quite large, because we perform array operations on large arrays, and that gives huge potential for parallelism, whereas the parallelism between array operations is usually little, but that of course depends on the exact program that you're executing. Then, if you're implementing an array language, and quite a few of us are doing that, then you can make the choice whether you want to exploit only the data parallelism or want to exploit both data and task parallelism. So first option would be to only exploit data parallelism, and the advantage of that is that you can then use a scheduler that is made specific for data parallelism. The other option would be to exploit both data and task parallelism, and what people typically do is that they implement data parallelism via task parallelism. So in this example, I have some data parallel operation B, and I can split that operation B into multiple tasks. And there are various ways to split such data parallel operation into tasks. I won't talk about that, but yeah, the downside of this is that we're now using a task parallel scheduler to schedule this data parallel workload. And I think, yeah, all the languages that are present here fall in one of those two categories. So I think SEC falls on the left side, where they only have a data parallel scheduler. Futark is, I think, on the right, where they use task parallel scheduler. Is that right? It's more complicated than that. Okay, and an APL, for instance? Okay, that's also complicated. Anyway, so there's kind of a gap that we have, and work assisting tries to fill that gap, because in work assisting we have task parallel scheduler for the task parallelism within a program, and then we have a data parallel scheduler for any data parallel operations within a program. And then we can exploit both forms of parallelism while still having a data parallel scheduler. So our work assisting scheduler is the link between a task parallel scheduler and a data parallel scheduler. And primarily we use the task parallel scheduler to distribute work. So whenever a thread needs new work to work on, it will use the task parallel scheduler, and it will try to claim a new task. If there are no such tasks available, then a thread will attempt to assist with the data parallel operation of another thread. And to do that, threads share their current data parallel computation, so that other threads can find this computation. Then the workload in such a data parallel operation is scheduled using a data parallel scheduler. Our scheduler is a dynamic scheduler, similar to work stealing and self-scheduling, which means that it schedules the workload during the execution. And this way it can properly balance the workload over the available threads. Specifically, this means that when we're executing a data parallel workload, more threads can assist in that data parallel workload. And this allows it to properly balance the work, and it basically provides the same flexibility as work stealing does, if you compare this to a system where data parallelism is implemented via task parallelism. And this is in contrast with existing schedulers for mixed data and task parallelism, because those typically fix the number of threads at the start of a data parallel workload, whereas we allow more threads to join a computation whenever they become available. This setup provides two main advantages. First is that data parallel workloads are scheduled with a data parallel scheduler, which is required by certain data parallel algorithms. And data parallelism is only exploited if task parallelism is not sufficient. As an example of that are zero overhead parallel scans, which I will in fact present directly after this talk, benefit from both those advantages because they require a specific order in which work is claimed in that data parallel workload. So they really require a data parallel scheduler because task parallel schedulers typically cannot guarantee that. And they have a fast single-threaded mode, which is faster than the parallel mode, and they operate in that mode as long as only one thread works on the scan. So hence it's beneficial to first exploit task parallelism and only exploit data parallelism if that's needed to saturate the processor. So that's a bit of the context that we're in. Let's now look at how we implement that. First, let's look how we model a data parallel workload. So we call a task with a data parallel workload a data parallel task. And in this example, we have several tasks, but task B is a data parallel task. And it consists of two phases. First, it has a parallel phase where we do the actual parallel work. And then we have a finish phase, which is executed when all the parallel work is finished. And the finish phase is executed by one thread. Example lifetime of a task can look like this. Thread 0 starts some work on a data parallel task, and it first shares that task so other threads can observe this task. Then it starts working on that parallel phase. Then after it has done some work, thread 1 finds this task because it was looking for something to work on, and it will assist in this task, and it will also help in the work phase, and thread 2 will then also do that. And at some point, all the work is being claimed, and a bit later all the work is finished, and then those threads will exit from the work phase. And thread 1 is the last thread to exit from the work phase, and that thread will execute the finish phase. Typically the finish phase will start other possibly data parallel tasks to continue the computation. So let's first look at this parallel work phase. I should say this is the only slide that contains some actual code, so I hope you can deal with that. So for the work phase or the parallel phase, we need to define a work function which describes what should happen there. And this function is called by the thread that starts this data parallel operation and by any threads that assist. It gets several arguments. First is a pointer to some data, and that's whatever data you need for this task, similar to the context of a lambda function. And this function will then, in a loop, do some work for block I, and that variable I is first assigned the value of first index, and first index is the index of the block that was claimed by the caller of this function. So the scheduler first claims one block, and then this thread will work on block first index. And when it's done with that, then it will, via an atomic increment, claim the next block. And this is basic self-scheduling that you may have seen before, dynamic self-scheduling. And you can also have other data parallel scheduling algorithms, but this is just a simple example for that. Then at some point all work has been claimed, because we're now with this atomic fetch and add constantly claiming more work, and at some point all work has been claimed, and then we should inform the work assisting scheduler that all work has been claimed. And we do that by calling this function signal task empty, which essentially tells the work assisting scheduler that it should not tell other threads that they can assist on this task. So it will stop sharing this task to other threads. Then, where the comment is we do the work for block I, and that should be sufficiently large amount of work to not have problems with scheduling overhead. So we typically implement some kind of tiling or some blocking. And then do work for all the elements. And to make it concrete, I can, because this is the basic boilerplate that you would need for any work function. To make it concrete, I can now convert this into a work function for a parallel reduction or a fold. To implement that, I would need to add some values to data, because I need to have an input array and I need to have a place to store the output. Then I want to store the sum for all the work of one thread in a local variable. So that's what I do in that variable local sum. Then at the place where I would need to do work for element k, I read that value from the array and add it to the local sum. And at the end, I add the local sum to the global output. And then when all the threads have finished the work function, we know the total reduced value of this array. So that's the work phase of a data parallel task. When all the work is finished, we call the finished function, and the finished function is executed by one of the threads that was working on this task in the parallel work phase. And in this finished phase, we typically spawn new tasks, which could be data parallel tasks. And that, of course, depends on the program. So those are the work and the finish phase. And in the beginning, we need to share this data parallel task such that all the threads can observe this task. And we do this by maintaining a global array containing the activities of all the threads. And this array is also called activities. And when a thread is working on some data parallel computation, it will announce that in this array. So it could, for instance, be in this example that thread 2 announces that it's working on a parallel reduction. And then any other threads that have no work for their own to do can assist in this parallel reduction. Well, we need to make this a bit more concrete, so let's see what we need to store in such a task object. Well, first we need to store the function that any assisting thread would need to call. That's the work function. We store a pointer to that function in the task together with the data or context for that function. Then we need to be able to communicate how much work has already been claimed, and for that we store a work index in the task together with the total size, so the number of blocks for this data parallel computation. Then we also need to know when all the work has been finished, because now we can see when all work has been claimed, but we also need to know when all work has been finished. And for that we keep track of the number of threads working on this task currently, which is kind of the reference count of this task. And we store that in the field active threads and in activities. So we split the reference count essentially over two places for a reason that I'll explain later on. But if you've ever done something with concurrent reference counting, then you may have seen this before. Then finally, we store a pointer to the finish function, which is called in the end. So now we can do a small simulation of how the work assisting scheduler could execute this task. So this task is now shared in activities, so any other thread can find this task. And when it finds this task and wants to work on it, then it will increment the number in activity. So that's currently a 0, but when another thread finds it, it will increment it to 1, and perhaps another thread joins, and then it becomes 2. These threads will gradually work their way through all the work for this task, and they do that by incrementing work index. So that's currently 1, and that will increment to 7, and so on. Oh. 15. And at some point, there may also be another task that becomes available, and another thread is working on that, and that will also increment the work index of that task, which will eventually finish. And then perhaps that thread that just finished that task will also start assisting on this data parallel task. So now there are 3 assisting threads, so 4 threads in total working on this task, and they will eventually increment work index to the last block. And at this point, this task doesn't have to be in activities any longer because all work has been claimed, so no other thread can help. And we then remove this thread from activities and move the reference count to the task object. So now we'll store 4 inactive threads, and then whenever a thread is done with this task, it will lower active threads, and eventually that becomes 0. Then the finish function is called, and then the task is deallocated. So you saw that I did some weird things with that reference count because it's placed in 2 locations, and that's because we're now dealing with concurrent reference counting. And in concurrent reference counting, you can have annoying race conditions, and we can prevent them if you can assure that incrementing the reference count and acquiring the pointer happens atomically. And we can do that by storing them both in the same word. What we concretely do is that whenever we increment the reference count, that happens in activities, in the count in activities. When we decrement it, we do that on the active threads in the task object, and this function signal tasks empty, which is called when all the work is claimed. That moves the reference count from activities to active threads. This is essentially a simplified version of the split reference count technique. If you want to know more about that, then here is some suggested reading. Then we did some benchmarks. First benchmark was lower-upper decomposition of matrices. We did this of multiple matrices at the same time, where the outer level of outer parallelism is that we're doing this on multiple matrices at the same time. And the inner level is the parallelism within one matrix. And the outer parallelism is implemented as task parallelism, and the inner as data parallelism. And here are some results for that. So we did this both on an AMD processor and an Intel processor, because scheduling may differ per machine. And on the left we have 1 matrix, and on the right we did this for 8 matrices. And as you can see on the left, it's difficult to execute that in parallel because there's just not enough parallelism. Whereas if you have 8 matrices, then it's a lot easier to exploit the parallelism. So the red one is our implementation, and then the purple open circles is an implementation with work stealing, and then the others are OpenMP, using the Clang implementation. And yeah, we're competitive with, are better than the alternatives. Especially on the right, it's interesting that we have 8 matrices, but this also scales to more than 8 threads, so then we really need to use both levels of parallelism. Then we also did a compaction benchmark. I'll quickly go through this. Compaction was one of the algorithms that had a special single-threaded mode. But yeah, more on that in the next talk or in the paper. Because I'm also running a bit short on time. Then finally, Quicksort. Quicksort is a divide and conquer algorithm, and we implemented partitioning as a data parallel operation and the recursive calls as a task parallel operation. And the contribution of data and task parallelism varies throughout the execution of the program, because in the beginning there is one large data parallel operation, and at the end there are many small tasks. And the scheduling algorithm should work well both in the beginning and in the end, of course. So here are the results. Again, the red line is our implementation, and we compare that with work stealing, which are the open circles, and OpenMP implementations. And the green line is one where we do partitioning sequential. And you can see, first of all, that scales poorly, and that we are competitive with work stealing implementation and one of the OpenMP implementations. And those are the results on an Intel processor. I think the OpenMP implementation also had some higher single-threaded performance, which made the comparison a bit harder here. But yeah, to conclude, work assisting provides the link between the task parallel scheduler and the data parallel scheduler, such that you can use both in the same program. It first only exploits task parallelism, and when needed, it exploits data parallelism. And yeah, work assisting is competitive with or faster than implementations that handle data parallelism via task parallelism and use work stealing. Thank you very much.
Questions?
Thank you for the nice talk, Ivo. My question is, what do you do if you have multiple tasks that do data parallel operations? How do you split the machine?
Okay. So if you have multiple data parallel tasks, then there will be multiple entries in activities. So then you'll be in a situation like this one. And if a thread now is searching for a data parallel task, then it will traverse activities in some order. And the order in which it traverses that will denote whether it finds the left task or the right task first. Which is somewhat similar to work stealing. If you are in work stealing and you need to claim a task from another thread, then you'll traverse the list in some specific order, perhaps randomized order, in a specific direction. And you can tune that perhaps also with a NUMA architecture to make sure that you choose the right one. But in the end, we just choose the first task that you'll find. But yeah, you could do more sophisticated things, perhaps. Yeah. So the implementation that we do, that we have in our benchmarks, is that you traverse the activities array starting at your own thread index and then going left or right. So half of the threads go to the left, half to the right. It's a bit of an ad hoc order, perhaps, but it worked well in our benchmarks. But we didn't do experiments to see if a different order would be better. I guess a randomized order would also be fine. There's some choices to be made there.
Right. Me next. All right. So one thing I always find challenging when writing these work stealing schedulers is figuring out the right chunk size. In your one benchmark, it seemed like it was hard-coded. Is that just what you do, or do you have something more advanced?
Yeah, that's a good question. So in work stealing, when you split tasks, you should at some point also decide how large those tasks should be. And we somewhat have a similar problem, perhaps slightly easier problem, because in the work function, you also split the work into blocks, chunks, and you should tune that. In our experience, you can somewhat easily find the right size by running the program on a very large input size and starting with a large block size and just lowering the block size until you see the scheduling overhead. Because then you'll find the block size at which the scheduling overhead is just only just invisible. And then you can find a appropriate block size. There are also alternatives because this idea of self-scheduling has been around for a lot longer. There are also, I think it's called trapezoidal self-scheduling, where you in the beginning have a larger block size and the block size slowly decreases. So that at the beginning you have a large block size, which gives you low overhead. And at the end you have a smaller block size, which makes it easier to balance the work near the end. Because in the end it's important that work is properly balanced.
All right, thanks very much. The next talk, guess by whom, where we're going to learn about zero parallel scans. So, Ivo, please go ahead.
Yeah, quickly need to switch. Okay, so hello everyone again. So I'm still Ivo, and I'm now going to talk about zero overhead parallel scans for multi-core CPUs. This is based on a paper that we presented earlier this year at PMM. So yeah, the work is about scans on CPUs, and we've heard scan already a few times today, so that should help. But just to make sure everyone is on the same page, a scan computes the prefix sum or cumulative sum, which means that for each element it computes the combined value of our prior elements. So very simple example, if you have an array of 10, 11, 12, and 13, then the scan could be that the first element is 0 because there are no prior elements, then the next is 10, 21, 33, and 46. And there are various variants of the scan, because now I didn't include the value at the same index, but you could include that. You could have a right to left scan. So there are various variants of that. So you can execute this in parallel if the operator is associative. It's similar to parallel reductions. And yeah, you see scans in many parallel algorithms, including algorithms to filter or compact data, or as we've also seen, to partition data. It's used to flatten nested data, for sparse matrix multiplication, also in computer graphics, and in the break I quickly added parsing as another example, because that's also an example of scans. So just to make sure everyone sees one example of that, I have this example to filter data, but it's somewhat similar to partitioning that we've already seen today. So I'll quickly go over it. To say that we need to filter this array and only preserve all the even elements of this array, then we can first map over this to compute this whether an element is even. Then we get this array. Then I can perform a scan over that. And then for each even element, I now know where that element should go. For instance, element 36 has value 2, which means that it should go to index 2, because there are 2 elements before that that are also even. And I can do that with a scatter or a permute, and then I get the desired output. Then, yeah, we're talking about performance. We're talking about parallel scans. And yeah, it is possible to execute scans in parallel. And parallel scans are also faster than sequential scans if you have multiple threads. And yeah, you may have a machine that has like thousands of threads, and then you might not worry about this. But if you have a more real machine, then you might not know in advance if you have multiple threads available for this parallel scan. And if you take existing parallel scan algorithms and execute them on a single thread, then they're asymptotically as fast as a sequential scan, but they have a constant factor overhead over a sequential scan. I think it was around 50 to 70% performance over a sequential scan. And yeah, so the main question is, do we have multiple threads available? And you might not know that in advance, because the processor may also be executing other tasks. So for instance, it could be that we have 4 threads which are all executing some task, and then at some point thread B needs to start a scan. Well, in this case it's clear that we can execute a parallel scan because thread 3 is also available. So we can let them execute the scan together, and then will be faster than a sequential scan. But what now if the situation looks like this, where thread B wants to start a parallel scan, but it's the only available thread? At this point, we don't know if it's worth to start a parallel scan, because it could be that in the near future, task C and D both finish, and then we have 3 threads available to work on this scan, and then we're probably faster by doing a parallel scan. But it could also be that task C doesn't finish soon, and it could be that task D does finish, but that we then need to execute a different task. So it's difficult to predict if a parallel scan would be worth it. And we introduce those zero overhead parallel scans. First, if you compare this to parallel map or parallel reduction or fold, they already have practically zero overhead. If you take a parallel map or a parallel fold and execute that on a single thread, then it will be about as fast as a sequential map or reduction. And we can just start to execute them in parallel without knowing whether multiple threads will be available. And that's not the case for existing scan algorithms. Hence, we introduce parallel scan algorithms with no single-threaded overhead, or practically no single-threaded overhead, that are robust in changes to the number of threads. They allow more threads to assist in the scan after its start. So some terminology. An aggregate of a block is the combined value of all the elements of that block, and a block is a part of the array. A prefix is the combined value of all prior elements, and the goal of the scan is to compute all prefixes. And we assume left to right scans for simplicity, but it also applies to right to left scans. So we introduced various algorithms. The first one is based on reduced and scan, which is a classical three-phase scan algorithm. And so as a scan, we get some input, and we should compute the output. And I visualize them both here on this slide. And what reduced and scan does in phase one, it reduces all the blocks to an aggregate. So the total sum of all the elements in the first block gets a certain value, and we do that per block. And the colors in this visualization denote the different threads that are working. And those different threads will gradually work through this array until they have computed all the aggregates of the blocks of the array. Then we have a series of aggregates, and we perform a scan over these aggregates. And we typically do that sequential because we just have a few blocks, so it doesn't make sense to do that in parallel, depending on your setup. And then we now know the prefix values of all blocks. And then we perform a scan per block, starting at that computed prefix value. And again, this happens by all the threads. So that's how a reduced and scan works. And let's now introduce our assisted reduced and scan. Our assisted reduced and scan is essentially a sequential scan assisted by a parallel reduced and scan. During phase one thread works from the left of the array, and that thread executes a sequential scan. All the threads work from the right, and they perform the first phase of a parallel scan. So they perform the reduce phase. In this case, the orange thread is working in the sequential mode and starts from the left and directly computes the output for its part of the workload. And all the threads work from the right, and they perform a reduction until they meet somewhere in the middle. Now at this point, the output for the first three blocks is already ready. And we only need to do some more work for the last 5 blocks. So we need to perform phase 2 only on those 5 blocks. And more importantly, we only need to do phase 3 on those 5 blocks. And the thread that worked in a sequential mode can again help in phase 3. So as you see here, we did fewer work in this example. In an extreme scenario where there's only one thread available, all work would be handled in the sequential mode in phase 1, and we would have practically 0 overhead. So to evaluate this, we did some benchmarks. This is a benchmark to perform a scan on a large array, and the yellow line is the standard reduced and scan, and the orange line with the open boxes is assisted reduced and scan, so our algorithm. And you can see that on one thread, it has a speed of exactly 1, meaning that it's exactly as fast as a sequential scan. And if you have more threads, then it's still slightly faster because we did a small part of the work in a sequential mode in phase 1, and thus have less work to do in phase 3. I was aware that 1TBB also has a somewhat similar optimization for single-threaded performance, but that optimization only works for single thread performance, because on more threads that doesn't give a significant benefit. However, this is not the fastest scan algorithm. That's the chain scan, as you can see here. And let's now take a look at how chain scans work. So chain scans are the state-of-the-art algorithm for scans on GPUs. And in this work, we show that it's also suitable for multi-core CPUs. So in the chain scan, we again distribute the array in blocks and let all the threads claim blocks. And after claiming a block, a thread will reduce that block to a single value, to an aggregate. And after it has computed that aggregate, it will share the aggregate. And then it will wait on the aggregate of the previous blocks to become available. So thread 1 can, after it has reduced the value, perform a scan over that because there are no prior blocks. But thread 2 needs to wait on the aggregate of thread 1 before it can perform its scan. And when it has that value, then it performs a scan. Then thread 3 also needs to wait on the aggregate of both thread 1 and thread 2. And then it knows its prefix, and then it can execute a scan. So you see that there is some synchronization overhead here. But this continues. So after the first 3 blocks are ready, threads will claim more work and continue this same process of sharing an aggregate, waiting on the prefix to become available, and then performing a scan. Then there is some synchronization cost. The chain scan with decoupled loopback reduces this the impact, and see the paper that introduced that, or our paper, for more information about that. But yeah, as I said, this is the state-of-the-art scan algorithm for GPUs. And on the GPU, this works well because we can store a block of the array in registers. Each block of the array is handled by a thread block. And in the thread block, we have many threads, and each thread has its own registers. So we can store all the values of a block in registers. And we can thus remember all the values between the reduce and the scan phase, and thus read each element only once. And typically, memory bandwidth is the limiting factor for a scan, so this is really beneficial. However, on the CPU, we cannot just store them in registers, because each thread has only a few registers, and then we would have a very small block. But instead, we can store them in level 1 cache by choosing the block size to fit in L1. And then all the values are stored in the cache between the reduce and the scan phase, and we only read them from main memory once. And then we get the same benefit. So that's how we adapt chain scans to CPUs. Let's now make them zero overhead. So we call those scans adaptive chain scans. They start in a sequential mode, and as soon as another thread assists in this scan, then they adapt to parallel mode. When a thread has claimed a block, then it will check if the prefix for that block is already available. If that's the case, then it performs it as a sequential scan. And if that's not the case, then it will perform the usual reduce and scan stages of the chain scan. So let's see that in action with some examples. So it could be that we start with only one thread available, and then we handle the first block in a sequential mode, we handle the second block in a sequential mode, and then another thread also becomes available and joins this computation. So what that thread does, it claims block 3, and then it sees that the prefix of block 2 is not available, so thread 2 will work in the parallel mode, and thread 1 will later then claim block 4, and that will then also switch to a parallel mode. In an extreme scenario, it could be that we are always stuck in the sequential mode, and then we have practically no overhead, because the entire scan is handled as a sequential scan. And it could also be that we directly start with many threads available, and then the entire scan, except for the first block, is handled in this parallel mode. Then, to go back to this benchmark, we see that indeed on one thread we have no overhead. We're as fast as the sequential scan because the open circles are our adaptive chain scan, and the red closed circles are the standard chain scan. So on one thread, we have no overhead, and on many threads, the adaptive chain scan is equally as fast as the chain scan. And the reason for that is that we only optimized for the sequential mode, which doesn't do anything if you have multiple threads available from the start. In the paper, we also have an analysis of the memory bandwidth to show that those scans are really close to the memory bandwidth that's available on the processor. So to conclude, we introduced assistive reduce and scan, and in the paper we also introduced assisted scan then propagate, which is another classic three-phase scan algorithm. Those are based on reduce the scan and scan then propagate, and in phase one thread performs a sequential scan, and it's assisted by all the threads performing phase one of a parallel scan. And then in phase 2 and phase 3, we have less work to do. It has 0 single-threaded overhead and slightly better multi-threaded performance. And then the adaptive chain scan is based on the chain scan with decoupled loopback, the state-of-the-art algorithm for GPUs. It reduces memory pressure at the cost of more synchronization. It starts in the sequential mode and adapts to a parallel mode, which gives it 0 single-threaded overhead. And it's faster than the classic three-phase scan algorithms, also on CPUs. Well, read the paper if you want to see the pseudocode for the algorithms, see benchmarks for compaction or filter. If you want to see the memory bandwidth analysis, we also have an analysis of the ratio between the sequential mode and parallel mode for the three-phase scans. And we explain the decoupled loopback of chain scans there. And you can also have a look at the papers that introduce reduced and scan and the chain scan. And that's all I had to say.
Questions?
I'm curious whether this the assisted technique might generalize to GPUs at all when you have one lane versus a core a block of threads to work with.
That's an interesting question. So on a GPU, you're obviously in a different setting because you have many more thread blocks. It could still be useful to do something similar to this. Because in general, if you're executing a scan on the GPU, you can assume that you have enough things available. But what if you're executing a scan over a matrix and you want to perform the scan per row of the matrix? Then it could be that you could just assign one row to each thread block, but you could also do something with assisted reduced and scan, where you, in the beginning, just assign one row per thread block, but have the option that multiple thread blocks cooperate on one row. And then I think the assisted reduced and scan could help in certain configurations.
I had a question about the SIMD features of the CPU. Are these benchmarks leveraging the SIMD features on the CPU when you're analyzing the memory bandwidth?
I think I have compiled it for native, so then it should use all the SIMD instructions that are available.
Okay, because do you know how that has changed over time? Because I think we did some benchmarking a while back, and it seemed like once you started leveraging SIMD properly, without threading, you immediately saturated the memory bandwidth of the CPUs, and threading didn't actually gain you anything.
That's somewhat true. Like, you don't see a lot of scaling because you quickly hit the memory bandwidth of the processor. So yeah, here you see that the three-phase scan scales to 2, and the reduced or the chain scan scales to about 3 times. So you don't see a lot of scaling because you quickly hit the memory bandwidth. But there is still some scaling possible. So this is on an Intel processor. We also have an AMD processor at work, and there it's scaled less. It's a bit older processor. But yeah, that really depends on the processor in the end.
The scans are implemented with SIMD operator. Like, I assume it's a prefix sum that you're benchmarking.
Yeah.
So those are implemented using the SIMD scan operations.
So I did turn like as architecture native, so the compiler should be allowed to emit any factor instructions that are possible. I didn't inspect the assembly to see what it's actually doing, but I would expect that it's doing factorization over this. But yeah, if you compare this, for instance, to, I didn't do a lot of experiments on that, but on my laptop, Apple laptop has a lot more memory bandwidth with Apple Silicon chips. So you do see a lot more scaling there than you see on this x86-64 processor.
Thank you for the presentations, very nice, both. I have more of a philosophical question. So it's nice that your mechanism is able to combine sequential scan with various forms of parallel scans and such. But what if, you know, like some sort of, you can optimize much better sometimes the sequential code than the parallel code, because, for example, you can fuse more aggressively, right, into folds and such. So this holds for one version of the code, but how would you, you know, like, so this is philosophical in the sense that give us your thoughts on how do you go about if you have multiple versions of code, like one code in which only this is parallel and the rest is sequential, and another code in which you have two levels of parallelism that can be, you switch back and forth between?
Yeah, interesting open question. So first thing that comes to mind is, because we've also been talking about fusion in the office, and it seems like that with a chain scan, you can also fuse more than with a three-phase scans, because three-phase scans need to be implemented in different kernels or different loops, and the chain scan is executed as a single loop or kernel. Yeah, so you can fuse a lot more if you have a chain scan. So that's part of your question. In general, it also felt to me like that there might be more algorithms where a setup where you both have a sequential and parallel implementation could work. Though the difficult thing is, which you also saw in the chain scan, is that during the execution of some sequential work, it should be allowed that at any point a parallel thread starts the computation. And you could perhaps that's also a good option, make your life a bit easier by saying that if, in this case, thread 2 starts working while thread 1 is still busy with some block, that thread 2 should then wait until that block is finished, so that you add some more synchronization. But yeah, that also costs something. Yeah, difficult to say in general. I would hope that this idea of having both sequential and parallel variant could be helpful for more algorithms. Yeah.
So how do you compute the sequential scan? Is that just a loop where you add something to the previous element, or?
The sequential scan is just a regular loop with one accumulating variable.
Do you know how, because I've imagined that it's very tough for a compiler to factorize that due to the loop dependency. There are any like parallel algorithms used for that? Or?
So I would expect that the compiler would just be able to detect this, because this is a standard scan. I don't know the names of all the, I think the Koch-Stone scan, can anyone confirm that? Is the scan that's used for SIMD level parallel scans. So that's, for instance, what's also used on a GPU within a warp and on a CPU on in SIMD level. So that's a different scan algorithm than what you see here, but that's very well suited for this vector, for those vector instructions.
All right, let's thank the speaker again. Let's carry on discussing, but there's coffee that wouldn't drink itself. So
want me to mention the original talk title?
I don't know. It depends who's in the room with us.
Well, if I say it and you don't say it, then it'll fall on me.
Yeah, it will be fine.
Anybody else we're missing? Okay, well, let's get started with our, is this the final session?
Yeah.
So this is the final session, and this is Jakub Horsky or something like that?
Yeah. Jakub Horsky,
He's
yeah.
going to talk about pointed programming, but the original title for this, I actually like the original title, which was Escaping the Pointless. And I figured let's throw down the gauntlet, you know, being a points-free programmer and pointed programmer. I thought it'd be fun. But, this is a more judicial.
All right. Thank you, Aaron. Oh, yeah, absolutely. Thank you, Aaron, for the introduction. Yeah, so my name's Jakub, hailing from the University of Cambridge. This work was done as part of my bachelor's thesis under the supervision of Professor Mycroft, without whom I wouldn't be here presenting today because I would never explain what I actually did properly. Well, maybe today I will. We'll see. So today we'll be getting points for free by embedding pointful array programming in Python, and it'll be a bit of a gimmick. So we have to sort of start with the setup to what we're doing. So Python, it's in the title. It sort of showed up during the discussion today. But the reason I'm doing this is because it is actually where people are doing a lot of array programming in a pretty specific way. And there are some things that probably have to be fixed about it. So the way you sort of do array programming in Python, you've got NumPy. This name has turned up a lot today. It's not a very interesting paradigm. To sort of jog your memory, this is how NumPy code tends to look. So we've got, you know, shape manipulations, sort of whole array operations, and sort of all the code, all the work gets offloaded to some other language in Python because it is too slow. And what is sort of significant here is that NumPy influenced like a ton of other libraries like PyTorch, JAX, and so on. And essentially all those, like, if I just gave you the snippet, you couldn't really tell me if it's NumPy or is it JAX or, like, those libraries essentially work the same. They just have different backends, really. And now, so that begs the question, why is everyone doing it this way? Like, is it really the best way that you can do array programming in every possible use case? I'd call it dubious. That's sort of, so hence the title, the original one at least. But sort of, let's sort of ask the question, like, if we could improve it, like, how could we improve it? And how do we sort of get to that point where people are actually using a different style than like NumPy-like, essentially? So sort of let's look at the sides of the different faces of array programming. It's really nice because it is the standard, so everyone uses it, everyone knows it, and the implementations that people actually have got out there are really good, I would say. Like XLA, every one of those libraries somehow is also using XLA. Perhaps not an accident. The sort of bad sides are that, like, from sort of a formalism point of view, it ends up having a lot of primitives. Like if you want to make a type system, you end up having more and more rules, and those rules can be quite unwieldy, especially with like broadcasting, and it's a bit messy sometimes. In particular, so far, Python still has no sort of standardized way of typing tensor computations. You just sort of, everyone is trying to come up with a way, but like my bet is that the paradigm just doesn't help. And then we've got the ugly, and this example is just lifted to try and be more objective. From a paper or from an abstract. And well, this is quite confusing, but there's some transposition going on. There's some messing with shapes. There's a reduction axis introduced that sort of gets summed over. And there's a lot of, I think the main problem that you sort of attribute here is the shape manipulation. Like there's something that's happening here to perform the right operation. It's perhaps not even obvious to you right now what this operation is. And I think the clear way would be to think like mathematically, like you'd probably write down the summation with an index and like say, oh, this is a matrix which has position ij, has this thing in there. Okay, so like, what if we could have, you know, a programming model where like, this is how the code looks? And this is the point for array programming. So sort of the snippet here now is sort of essentially how my calculus for point for array programming that I use throughout looks. This is not something that I've come up with. There's been tons of influences that sort of go in this direction, but essentially pointful array code explicitly names its dimensions and indices instead of just sort of manipulating shapes of arrays. And this is opposed to this point free code where we manipulate shapes instead. We use like combinators and stuff like that. And sort of the key idea here is that it's sort of like arrays as functions. Like the array comprehension can be thought of as essentially the lambda abstraction of arrays. And where is this showing up? Like the very initial place you see this, you would think of this is Einstein summation. And indeed, this is how the Python community came about to like sort of these sort of ideas. So this is an example like how you write a matrix product in Einstein summation with in some variation of that notation anyway. In NumPy, sorry, in Python, people like, in NumPy, there's already been einsum, which is just slightly generalized Einstein summation for ages. People weren't really using it, then people started generalizing it because they thought, oh, maybe it's a bit useful. So tensor comprehensions, einops is sort of the thing that actually people are using, like practitioners are using. I don't show einops here, but essentially like, it's like this einsum sort of stringly typed mini language. And then you sort of start putting shape manipulation, sort of generalizing that. The problem with that is that you can only generalize strings for so long before you end up with a whole another programming language. So what people actually did, or quite recently, Pashke and others made DEX, or published DEX, which is like a whole pointful array language with some value-dependent types, and it's pretty cool, the theory behind it. This is how the initial sort of snippet looks in DEX, so it's quite similar to what you might expect. And I don't go into DEX too much because it's just an example. Okay, you can build like a whole programming language around this idea, and that's sort of the point here. So there's obviously potential in the theory. Like we've got DEX. Also, here I rely on fsmooth. Also, SAC has had now tensor comprehensions. So all of these ideas sort of are popping up. But people, like actual practitioners, can only use like einops, which is like, oh, just some, it's a string mini language. You can only do so much. But what's really good about it is that it's framework agnostic, so like people across the ecosystem can use it. So like you can use PyTorch, you can use JAX, and so on. And it would be really nice to like have a pointful array programming ecosystem for Python, but I don't want to be the one to write it. Maybe one of you will, but probably it would be difficult to get anyone to adopt it. So the idea, the approach is to embed a pointful array DSL, like a proper one, like a proper nice library with an API, which you can describe as just NumPy, but array comprehensions, and then make a compilation scheme, which will actually take me from this pointful DSL into point-free array programs. So sort of, I can use it can directly call those existing backends to NumPy-like libraries. And this is sort of the key approach of this project. So sort of, and obviously there might be some, in case there's still some ambiguity on, is this the best thing to do? Like, does anyone really care about pointful? Here's a practical example of what someone wrote, or what is in the implementation of a graph attention network, so some attention-based architecture from a couple of years ago. So people are implementing these new architectures, and they end up having to write code like this, which is mostly just noise. The permutations, good luck saying if I made a mistake on the second last line, for instance, and I wrote 0312 instead of 0213. I don't think there's a mistake, but why not just write code like this? And this is ein, so ein just says, okay, define me a 4-dimensional array, BHUV. Those names have some meaning if you look at the, for the axes, for those indices have meaning if you look at the original implementation, but either way, it becomes much clearer what this is actually doing, what the transpositions are doing, what the broadcasting is doing. And the key fact here is that this is actually producing equivalent JAX code. The original code was JAX. This is also going to produce it. There might be some small differences, but it turns out that performance-wise, it's fine. Okay, so let's look at ein for a bit. So here's a bunch of examples of how you can use ein. Sort of basic things. First line, we've got defining an array just from numbers from 0 to 4. Then I can just say at index I, give me I, and the size is 5. Those sort of things. The outer product, the third example, that's sort of just saying, okay, define me a matrix which at index ij has u of I times v of j. All of this stuff, and all of this neatly can compile to NumPy-like, to calls to a NumPy-like library. In this specific case, this is purely functional, so I'm not like, I'm just picking a bunch of Python ASTs and like doing arbitrary things to them. This is like an actually well-behaved deep embedded DSL, which doesn't do weird things. It's deep embedded, so it's closer to like accelerate, like Haskell accelerate. So you have to introduce values to it and then evaluate them explicitly. So we're sort of working on, with a colleague, we're working on a different implementation, which will be a bit easier to use, but that's sort of future work. In terms of like the sort of types you're working with, and combinators are sort of primary here. You just got vectors.
Ein doesn't have multi-dimensional arrays. The sort of nice thing about the pointful style, because you get to index so much, you can essentially just think of multi-dimensional arrays as either scalars or vectors of other arrays. So that's sort of simpler. So that sort of makes it easier to integrate. Like, I don't know, I can have record types now because I can say this vector actually contains pairs of other vectors or something like that. So it becomes convenient to reason that way. And then scalars, which is typical stuff. We don't have rank polymorphism to keep things simple, but I guess you could do stuff, Fuvark-like stuff, like from the talks earlier today. The combinators, like, probably draw your attention to the first one. This is just the array comprehension. Given a function which, like, given an index gives you a value, you can get a vector of that value. The trick going on here is that if you don't provide the size, what Ein does for you is infers the size, so that keeps things simpler. There's also fold, which is just an index fold, sort of like a for loop construct, and reduce, which is sort of just added as a proof of concept that this scheme that I'm using generalizes to those sort of combinators. So this is an associative reduction. So these are sort of like Fuvark, Sanger, or the array combinators. You don't get this sort of stuff in NumPy-like libraries. You just do everything with broadcasting and batching or batch axes and a lot of weird stuff. So quite clean, I think. And this is just a slide to showcase a bunch of other features of this, sort of headlines. You can execute with a bunch of backends. You can have user-defined classes for your elements, which is not at all what you can do with NumPy. So if I define a class of points, then I can have a vector of those points. You can have static typing, which reasonably works with the tools people are actually using in Python. So this is up to like rank and polymer and those sort of user-defined classes. So it's sort of halfway there. Doing shapes is still really difficult. And there's also ways of integrating with existing framework code. So this isn't like just completely separate, completely independent. So that's about Ein. But now I sort of have to answer the question of how I'm doing the magic of going from sort of this sort of pointful language to a point-free sort of NumPy-like library. So let's start with saying what my source language is. So this is a pretty simple calculus just based on fsmooth. So this is something that has been used for devising like essentially pointful array methods for compilation, like for memory management, for automatic differentiation. So this is pretty standard. The key thing is we've got array comprehensions, indexing, and the sort of weird thing I have in this calculus is I separate out identifiers. I don't just have variables, I also have a separate kind of identifier called an index. So this is denoted with I, j, k, and so on. And yeah, I omitted a bunch of features here, which you just have to believe me, they end up working out. So why did I separate out indices and variables? So one sort of simple motivating example would be to look at whether we have rectangular arrays. I didn't really say, but NumPy we only really deal with like rectangular arrays of primitive data types, just to keep things efficient. For instance, this expression produces a jagged array, and we have, well, the inner array has a size dependent on the index in sort of the outer array. So this would give us sort of a pyramid-shaped array. This is not a great array. So what you can do with sort of having a separate kind of identifier for indices, you have a type check, which just keeps track of a separate environment for indices. And whenever you're in a size, you just don't allow sizes to depend on indices. And this sort of makes sense. Like the size of the array cannot depend on which element you're in. And this gives you rectangular arrays. And in fact, this has other nice properties. You actually get regular parallelism in general with the index fold stuff. And you also actually get a compilation scheme. Like the compilation scheme really just derives from this choice. So to sort of get a compilation scheme, so the way I sort of derive it is compositional. So I sort of want to have associate for every sub-expression of a phi term, so a phi calculus term, I want to associate some term in a point-free language. So we sort of start by thinking, okay, so here's an expression. The equality sign there, don't take it too literally. This is just what the thing evaluates to. But the sort of question I want to be asking is, like, this was a program. They didn't have any free variables or free indices. But what if I did have free indices? Like a lot of programs will have free indices. And a point-free program will not contain indices at all. So I want to get rid of them. So I need to be able to reason about what happens if there are free indices. What would happen with them? So if I just looked at the part 3i plus j, what is this? So from a denotational standpoint, this could be seen as like a function where if I give it an assignment to I and j, it tells me some value. But the special thing about indices is that they span over some set range. And I guess the gimmick here is that we have to set what the size is for those indices. So I will say that, okay, I has size 2, so it goes 0 and 1. J goes over 0, 1, and 2. And this allows me to actually say, this is sort of like a matrix. it's not really a matrix because it's ambiguous in what way would it be a matrix, but all the possible values this expression can take, given the sizes of those indices, can be written down in the matrix. And this matrix has this funny sort of labeled axes, like columns correspond to different values of j, and rows correspond to different values of I. And this sort of lists down all the possible values they can take. And in fact, I could write this matrix in two ways. I could transpose it, but this doesn't really matter. And yeah, the key thing here is that we have to set the index sizes. The way I actually reason about this is I just reason about it symbolically because an index is only bound with one size the moment it's introduced. So we sort of never mind this, but in the implementation, you just sort of substitute in the right size as defined. So there's a structure here of like these matrices with label axes or arrays with label axes in general. And this sort of leads us to having a compilation scheme which relies on computing these array-like structures. And these structures are called axials. And here's an equation which is a sort of daunting, I think, a bit. But what it's essentially saying, and which I sort of try to argue for, it's an intuition or sort of a derivation for saying that if I have a phi term, which sort of needs an assignment to variables and an assignment to indices, and it gives me some value once I give it those assignments, then this is sort of as if I said, okay, this indices should occur in this order. So for instance, there I selected I goes first and j goes first. So I is rows, j is columns. Then it's like a usual assigner of variables. And then I get all the possible values of this expression given any assignment to indices. Like, essentially, this is saying I can get rid of all the indices from the expression, sort of get rid of all those three indices, and instead compute all the possible assignments to, all the possible values given assignments to indices. And that's sort of the key idea, and this idea is encapsulated by the axial applicative. And I sort of elaborate how you define the axial applicative, but I'll just go with an example instead. So we'll have to say first what the target language is. This is essentially just NumPy, but abstracted. Like a common movement in Python is actually trying to standardize what this interface should be. It's called the Array API. Maybe one day they will succeed, but for now there's 5 different interfaces, so I had to pick one. So it's called YAR. So we've got shape manipulations, we've got some simple constructors, we've got broadcasting element-wise operations, just sort of standard stuff you might expect, but obviously no array comprehensions. Those are pointful. We want point-free program. So the compilation scheme will give us sort of an interpretation for every phi term. So it'll take us from pointful to point-free. As before, you have to sort of to represent stuff in a point-free representation because phi has 3 indices. That will sort of create arrays instead when you have to say, what is this array representation doing exactly? So this semantic equivalence here, this in the middle, is sort of saying, okay, so if I had a phi term initially and it has these 3 indices pi 1 through pi k, then the compilation scheme will give me a YAR term, so sort of a point-free array program, which computes all that array of all possible values given any possible assignment to an index. And this essentially is just saying, okay, so like this essentially gives me this compositionality that like I can bottom up compile the phi term into a YAR term. Yeah, and here the pi is sort of administrative. It's just sort of keeping track of like how am I representing those possible values? How am I representing that array? And I can pick my order myself. This ends up corresponding to the memory layouts depending on how you implement things, but yeah, that's essentially the idea. And I'll try to give a very brief example of this. So let's say the phi term is a of ji, and we add this to b of ikj. I sort of compile the sub-expressions, which are in this case a of ji and b of ikj, and I get some e prime and e double prime. And they've chosen some orderings for those indices, so I know what sort of arrays I'm getting from those e prime and e double prime. And now the final expression will look something like this. This is obviously also a comparison of how expressive pointful can be in comparison to point-free, because there's a bunch of administrative work we have to do here. So we have to first transpose the e prime's representation to get a representation in ij. Then we have to unsqueeze to introduce an axis of size 1 so that broadcasting works out. So we get something like I1j, and then I1j and ikj can be added together to produce whatever e was computing. And this is, this ends up corresponding in the axial applicative, which is this pattern which I try to fit in this compilation scheme into. This ends up corresponding to the left of the applicative, which is a very fundamental operation to the applicative. So yeah, in a way, the axial exactly encapsulates like this entire compilation scheme, because element-wise operations are most of what you're compiling. Okay, so we can finish off with some conclusions. First off, these two things are now sort of equivalent. I made the ein code a bit longer, but the NumPy code you've already seen before, so nothing too interesting to see there. The ein code has like fun properties that essentially allow us to program in a more functional way. So I put down some type signatures to maybe make it a bit easier to follow what it's doing, but here I separated out a function for computing the distance between two vectors. So this is the L1 distance, so the sum of absolute distances. And this fun thing here is that in a NumPy-like framework, this would be quite difficult to do it this way, because what you have to do in NumPy is you have to keep track of the entire array at a time. If I wrote this function this way, then you'll have to assume that, oh, maybe this array has more axes, maybe it has to broadcast through things. And here, in a pointful style, this sort of gets abstracted away. Here, in the last line, I'm just sort of passing every possible pair of rows of A into the function, and everything gets handled through by the compilation scheme. And this is sort of zero cost in the sense that like it doesn't matter that I made a temporary function here, because it really, in a deep embedded DSL, it just sort of works like a macro. So it gets erased at compilation time, we could say. And yeah, in benchmarks, it does well on a variety of tests. So these are used in FooVerk and DEX. It's a selection. Also some cases specific to deep learning, the first two. And this is sort of, yeah, it's within a small constant factor. That's sort of the point here. Where it's faster, this is mostly because I implemented a variety of optimizations. So there's some stuff which is done differently to the baseline, which I had to implement. But I think generally the goal was to get comparable performance, because whether it's better or worse also depends on what backend you're using. Yeah, and those are essentially those things. You can see the implementation because it's open sourced, and hopefully maybe someone will write a better one at some point, because that's what we've got. So here's a new pointful array DSL for Python, the first one, which is this general. And axials sort of allow us to take pointful programs. So like these techniques are being developed to point-free programs, which are things that are actually implemented. And because of this, I can execute it with different runtimes, so NumPy, PyTorch, JAX, TensorFlow, whatever. And yeah, it's essentially a reconciliation of those different kinds of ideas, both theoretical and practical. And so it's a best of both worlds. So it's sort of, yeah. And yeah, so that's everything. Thank you for listening, and happy to take questions.
So you had a graph for targeting NumPy. Do you have similar comparisons with PyTorch and JAX?
I didn't run them, but so I did run them in some cases. What tends to happen is that these benchmarks that were used for FooVerk and DEX tend to rely on patterns which I didn't optimize properly. Like for instance, stencil is something that you would never do in PyTorch, so it doesn't do well because of the indexing. In JAX, it does okay. So it's sort of, I think the comparison is a bit worse because those libraries are so domain specific that some of these operations just don't behave well in them. So for instance, if I tested attention in GAT, which is actually like deep learning flavored, which are deep learning flavored benchmarks, those work quite well. Like in fact, they can beat the baseline PyTorch, because the baseline PyTorch, for instance, uses einsum directly, and einsum does some extra work with regards to optimization, and this work can be done at compile time in ein instead. So there's some differences that essentially make that sort of comparison a bit subtle. Yeah.
So do you support local lead bindings?
So what do you mean?
So in expressions, do you have ways of having local names to things?
Oh, okay. So the way I handle this is, I think maybe not standard to Python, but I thought it was quite standard. So because the calculus is purely functional, so the phi calculus itself has lead bindings, but when I construct it, I just use a term graph representation. So I make it very simple. And then the way I think about it is that inserting lead bindings at that point is sort of like common subexpression elimination. And because of how simple the calculus is, I just do this with dominators. So dominators on a term graph tell you what is the essentially, dominators in a term graph tell you where should I insert a let binding so that this expression is computed as late as possible and kept for exactly how long it's needed. So it's not done on Python level because that would be quite messy, but there's nothing stopping me from, for instance, here when I reuse A, if A was a result of some more complicated expression, then everything would be handled properly. Like it would eliminate the common sub-expression and it will all be fine. Yeah, and so there's no exponential blow up that can be handled. Yeah.
And next we've got Brandon, who's going to be talking about the nanoparsing architecture in APL.
All right, hello everybody. I'd like to talk today about something that a new kind of parsing architecture that Aaron has basically pioneered and that I've been exploring, and let's just dive right in. So the background, what we should have in our head right now is basic recursive descent parsers. And the whole suite of techniques that we use just for traditional context-free grammars and parsing. And there are some sharp edges that say recursive descent parsing or LL parsers present that we would really like to overcome for more difficult problems. So like one in particular, there's sort of these context, you have limited context in recursive descent. So like error handling is known to be, is quite challenging. Yak, for example, produces terrible error messages. Type inference tends to be split out into its own phase, and you have to have like introduce this cut point, and you have to limit yourself to the kind of computations you're doing in parsing. And then doing sort of like static analysis or even like injecting some of your knowledge from analysis into your parser is kind of blocked from because of these limited contexts that you have. Then there's some pretty sharp edges around affordances too. Like debugging can be quite challenging whenever you have like a very deep call stack and you're jumping around between all of your mutually recursive functions. Then your the behavioral reasonability, it's like in order to figure out how particular inputs will affect the runtime behavior and the sort of data flow through your program is not just manifestly obvious. And then if you want to make some sort of change to your input language, if your problem domain is not completely formalized and you're trying to you're incrementally wanting to implement it, or even if it is formalized and you just want to go piece by piece and implement it, it's somewhat challenging to make incremental changes in knowing what effects they're going to have. And then finally, the scalability of these languages, and this is more like sort of, especially whenever you don't have a formalized system or you're thinking about expanding out, it's quite challenging. Like to reason about performance, I mean, performance on parsers is not. I mean, we've had talks about that today, so we know that's a challenging problem. Your platform independence. We want to be able to run parsers on GPUs, CPUs, on distributed systems. We want to be able to have all of those things, but it's not a solved problem. And then have scale between your domains. So like if you have if you start off with some business problem or some non-formalized problem, and you can come up with a small little hack like some regex to solve it, and then over time it gets more complex, and you start to implement. You run into a context-free grammar, and then sometimes context-sensitive grammars, where your problem is just hard to scale with these traditional techniques. So we have this trifecta of context, affordance, scalability that gives us these problems, and that's what we're trying to address with this nano parsing architecture. But first, let's look at some of a particular instance of this, where we are looking at APL. But it's not limited to APL. I mean, I've written a YAML parser using this technique, and I use the same technique to implement the MetaMath language parser. But APL in particular has a very perverse context where there's runtime parse errors. So there's the famous ABC problem where depending if you have A, B, and C are different variables, the parse trees that can generate of the string A, B, and C has a combinatorial explosion. There's like 10 of them. And then there's mixed scope, there's dynamic and syntactic scope, or lexical scope that sort of interplay in between each other. Then there's quite adverse affordances to parsing APL as well. There's like no black and extant parsers do exist, but they're not so great. And there's no black box introspection on sort of like in production systems these days. There's extensive eval usage in production code. It's all over the place as standard techniques. And then there's no formal specification of the language. And in fact, the standard implementations are known to be buggy, so we can't take any particular implementation and call that the ground truth. And then we have quite some challenging scalability issues in APL for an APL parser. There's millions of lines, or the code bases in production right now have been around for decades and have millions of lines of code. These are legacy systems, so that means that we're running on multiple different platforms, and we have multiple different dialects of APL that might be mixed in together in the single code base. And then the language is not context-free. So what do we propose? We propose nanoparsing. And so let's zoom right into what that is. So the catchphrase for this is we transpose the computation over the data, atop the data, into the data atop the computation. So in a traditional recursive descent parser, you have like a little window of context. You're a window of like K around whatever token you're on, and you have your entire recursive functions, and you perform a whole bunch of computation over that little window, and then that window slides along. Whereas in nanoparsing, we flip that on its head, and then we take a small piece of computation, and then run that over the entire input. And then we do that again and again. So we're doing multiple passes, but each of those passes are really tiny. That's why it's called nanoparsing. So it's a chain of these back-to-back nanophases or nanopasses that they maintain. In this particular, maintain a global state of the parse tree that incrementally refines what your AST looks like. So instead of trying to like insert tokens into an existing sort of empty tree, you can start off with different tree structures and slowly refine that to get it closer and closer to what the actual language implements. And then since we're using APL, we use a lot of APL codefund style tree wrangling sort of techniques. So there's the using a parent vector or even just a depth vector to represent your trees, and then a bunch of idioms that are sort of manifestly data parallel to implement tree wrangling stuff. So yeah. And so this is kind of what it looks like. So you start off with this APL function up top. You can feed this into codefunds, and this was like a recent implement or recent commit of codefunds, and you can throw this at the top, and we entered at a few breakpoints, and then you can just output these different trees at different points through the parser after certain phases. So like at level 1, you see after the lexer, right? But what's interesting is like the lexing itself is not, normally lexing just like gives you a stream of tokens. But you can see here we kind of have a little bit of depth information. We kind of have a tree. I mean, it's pretty stubby forest here, but we have that. And then go to phase 2, after we parse brackets, you can see we get a little bit more depth information, right? And then after function specialization, you can see that we have 2 subtrees here that are isomorphic to each other, sort of like different specializations of the particular function that we defined up there. And then at the end, we get this complete AST. Max, yes? The namespace. Right, those are the functions, right? That's the function f, I believe, up there, right, that we define. Okay, so this is APL. Bask in its glory, right? This actually is not an APL parser. This is from my own YAML parser. This is the entire parser, right here. Like this is it, and it starts from, and the data just flows from the top to the bottom. So you get a list. You just get a list of characters from the top. Phase 1 normalizes the input, and then each line is a phase of the parser. And you're not expected to understand this, right? I mean, it's written in a way so that someone who knows the problem domain well, and after we talked, like, you would be able to sit down and read this code and glean information about YAML and about certain different constraints and novel type theoretic information about parsing parsing YAML by reading this. But it's straight. It's just every single line. The basic thing that I want you to get out of this, other than fancy pictures of a lot of APL, is that it's just from line 1 to 22. Each line is a particular phase, and then it refines the AST as we go down. And I'll move on to this is an excerpt from Cody Funds. So now at this point this is parsing APL, but this zooms into a single phase. And in the parser, like previously where we saw each phase was just like in my semi-toy implementation here of YAML parser, this is, a more complicated. You can see it's multiple lines, and even though it's a single phase. But we have a bunch of interesting things going on here in our parser, right? So one, you can see there's several different places where we're doing error checking. And these error checks will underline in your code and where your problems are and give you very nice error messages at those points. And then through here, so what this piece of code is, just a standard problem for finding your regions of brackets and parentheses, right? And then it's going through finding the regions where for each expression where those might occur, and then inside this block here, it's going through there and finding the parentheses and adding the type information to some global state. And what's interesting is that we can have this interplay between where we have a local view of our data, where we're looking at each individual expression and we're just zoomed in on that. But then at the same time, we can take the information that we gleaned from those local pieces and inject them into the overall refine our AST by injecting that information into it. And then after this phase is done, then we now have effectively declared a type theoretic change or transformation on our AST. Once we come in, we know that we kind of know what those regions with parentheses and brackets might be. And then when we come out at the bottom, we have this line 13 here is literally erasing the closed parentheses. So because we've already taken that information and we've wrapped up the stuff inside parentheses and put them in and wrap them up under a node. So we don't need this closed parenthesis anymore, right? So this sort of has all of these little pieces mixed together where we have global state, we have a linear data flow from top to bottom, but then we have some potential, each phase can have some sort of internal little recursion on it. Instead of having global mutually recursive functions, there can be local recursion happening, but yeah, and other than that, it's a linear data flow, and it has these nice. It's very easy to insert relevant error messages at any place in your code because you have all of the information that you could possibly need, and you can even this signal function here puts really nice line numbers and underlines and stuff on your error messages, which just beats Yak and stuff like this out of the water. So what does this give us though? What are the benefits of this relative to this trifecta of problems that we talked about? Well, we have sort of holistic context at every point in our parser.
So like we have orthogonal error handling, like you just saw, where we can insert very relevant error messages at any point in the code. We can perform arbitrary computations anywhere, right? So that means like you can do type theoretic analysis through your parser at any point instead of having to split it out into some other bespoke pass through your AST. And then we have sort of the ability to do global level analysis on our code base. So you can do like static analysis kind of level things and inject some of that information into your AST as you're going through parsing, instead of having to add different sort of cut points where you do like lexing and then you do another traversal with parsing and another traversal with his like optimizations or something. These can be interleaved in a way that's more natural to the expression of the language, where like at this point you have the information that you need, you have certain constraints that you need that you've already guaranteed, and you can just do it at that point instead of having to like split it across different regions of your code. Then the affordance is like actually using this as a developer is actually quite nice. Like this is how I learned APL effectively. And it's, we can do like stepwise debugging, which is really quite nice. You can just set a, if you want to know, if you suspect there's a problem somewhere in your AST and you kind of know where it's happening, like if it's in parentheses or something, you can just put a breakpoint there, and then you feed your input, and you'll stop right at the point where you know exactly that your constraints, exactly what constraints, what your AST should be at that point, and then you can just have all of the tools of your entire language to inspect what your AST looks like, what is the data that's coming in, what are your types, and all of that at that point, which is really challenging in like Yak or something. And then we have, this is basic, and then since we have a linear data flow, since we have, anyway, we have linear control flow through the entire code base. That means you just start from, like, if you want to know how your data goes in, you just start from the top of the code and you just read straight from top to bottom. Super easy to reason about. There's like almost nothing to reason about in the control flow graph, which is really nice. And then that combined with the debugging makes it very, very nice to just incrementally extend your system, right? So like the way that I implemented the YAML parser was just to write a simple test, like for like empty input, and then come up with the design of what I thought the AST should be for that kind of thing, implement it, and then just slowly, incrementally add little tiny features to my parser as it became, and bring it in parity with the spec. And the YAML spec has this like big document of 211 productions in order to implement it. And standard extant parsers of YAML have to introduce a lot of bespoke other productions on top of that, as you normally do, in order to implement. And it's really, really hard to reason about. But since you can extend it like this, it makes it much easier to implement a parser. The barrier to entry is really low. And then it also is quite scalable. It allows your system to be quite scalable. I mean, using especially these codefund style tree wrangling idioms and stuff means that you're almost manifestly GPU compatible. And then since we have, it's not introducing particular parallelism primitives into your parser, right? So it allows you to be somewhat platform agnostic, right? And so you can sort of especially if you fed this through into codefunds or something, like, and you're using APL, you can have different backends that target different architectures. You can be on the GPU, you can be on the CPU, you can be on other host systems with different architectures or whatever, without having to put your certain parallelism primitives and stuff in your parser explicitly. And then this is tied in, like the last one is incremental expansion, which is more like, so we talked on, it's different than extensibility in the sense that if you have a problem domain that you're trying to solve by implementing a language, you can start out with you tend to start with like a simplified view of what the problem is, and then slowly learn more information about the system. And as your problem gets more complicated, you might start crossing different domains of language classes. So you might start off with like a context-free grammar that you think that you could implement your language with, but then you'll move into something like APL that's context-sensitive. And if you're using traditional architectures, you'll have to sort of, you can't take your tools that you're using from your previous for a context-free grammar and just slowly extend them into like the larger domain. You kind of have to you have these hard points. We have to throw away everything that you were using and then re-implement it because you've crossed into a harder problem domain. But with this nanoparsing architecture, you're not beholden to any of those particular constraints. And so you can incrementally expand the class of problems or the size of the problem that you are trying to attack. Oh yeah, I already went through all of these. But there's definitely some future work here. So if you're interested in this and you want to learn it, there's quite a steep upfront learning curve. That's just a cost you can't get away from. And we haven't done like extensive benchmarking on how this relates to a standard recursive descent parser that might be doing something similar. Like naively, you're doing multiple passes over your input, and so you would have, if you have like C number of passes or N number of passes, you would have a constant time increase in the amount of work that you're doing. But like each of these passes are a lot smaller than your traditional recursive, like the amount of work that you're doing on each little window in your recursive descent. And so it's not clear exactly how those two interplay. So we want to do a lot of extensive benchmarking and especially theoretical analysis. How does this relate to an LL star parser or something, or in the LLPQ or LLPQK parsers or something like this, right? And so we'd want to figure out that story and then look for use that knowledge to look for other opportunities for increasing the parallelism in your implementations. So like for Cody funds especially, you have a bunch of different phases and that happen back to back, but if you compile Cody funds with Cody funds, you have opportunities where you could smash those phases back to back that are back to back and smash them together maybe, right? And then you can reduce this potential constant factor overhead. There's a lot of, we need to do at platform comparisons as well. We don't know we don't have a theoretical understanding of the different guarantees that, compiling for a GPU versus CPU stuff, we need to figure all of those out. And then more than anything, since this is kind of this architecture is not being used everywhere, I'm sure there's tons of low-hanging fruit and a lot of unknown unknowns. So I really want to get this kind of thing into you guys' hands and to see what you would do with it and how you would explore what it looks like to write parsers in this particular way. Yeah, thank you very much.
Thank you for a nice talk. So the aspect-oriented programming people have these terms, scattered and tangled code. Scattered where one concern gets just spread out over a lot of code, and tangled where you have one particular point in the code and a lot of concerns are competing for it.
Yes.
Do I understand you correctly? It feels like you're addressing and solving that problem in a sense where you get to write this very linear code where on each line you handle one particular concern and it's all very focused and factored in that way.
That's very much my experience of how it feels to use this architecture. I mean, that's very much on point, is each phase you're making these incremental, and this is specific to parsing, right? This particular architecture that I'm introducing here. But you can kind of like, especially if you need to introduce something into your code, you know that the potential things that can affect your code is all the code above you. And everything below you is just irrelevant, right? And so it's really nice to where your concerns might, or what things might affect you. It's much easier to find, and yeah, it's very much related to what you were saying. So thank you very much.
Okay. Right. I'm
I'm not sure how fitting of a question this is, but you're sort of comparing Yak, which is a parser generator, so you give it a file for the productions and tries its best.
Yep.
And maybe you have to mess with it a bit.
Yep.
And you're comparing it with a technique for writing sort of handmade parser that might or might not fit the specification. So are you saying that this is sort of a technique that people should use when they like want to make their own language and want to roll a parser quickly? Or like where would this technique be best applied?
So I think that you can, like, Yak is really nice if you have a simple language, especially if you just need like to knock off something real quick. But if you need something that's production ready, you need to have like, you want your users to have nice error messages and things like this. Then it turns out that the code that is produced by Yak, you need to do a lot of work on it. So for the kind of problems, I'm proposing that this is in sort of an industrial grade architecture that is both really nice to use, but also has a lot of nice affordances for making a robust system that you can just start getting up with quickly once you learn the architecture.
Okay. And how would you ensure that it's equivalent to what a parser generator would give you? Like if someone does have a specification, then... Oh, yeah, sorry, yeah. That's right.
It's a good question. No, yeah. I want to keep it on time. So the next speaker is it Yuso? Is that the right way to pronounce it? Yeah. Yuso on structural under and GPUs. So.
So yeah, I guess I could start the talk about talking a little bit about my background from APL and kind of like what I'm looking for it is that kind of like the way I see APL
Hello? Can either of you hear me? Okay, can you say something, Juan? Are you sharing? Are you going to be presenting slides? Yes, please. Yes.
Okay, okay. Yeah, I will project it now. So, like, should I start now? Is there everybody in the room hear me?
Yes, we can.
Okay, so I will start now. Okay, hello everyone. So my name is Buck, and today I will present the landscape of formal verification in APL with a review and a case study in quantum computing. This is a joint work with Feng and Santiago from National Center for Supercomputing Applications. So in this talk, we will provide two main contributions. The first one is that we will provide some preliminary work on formal verification of QAPL programs. QAPL is a quantum programming library written in APL. And also, we want to show that quantum circuit expression and simulation benefits from languages where linear algebra is expressed naturally, like APL. Secondly, we want to present our approach when we are applying SMT solver to verify QAPL programs written in a subset of QAPL. This subset only contains defuncts only, no external libraries. It also provides interpreters to translate APL to Z3, which is also a SMT solver. We also show some identification of invariants, pre and post conditions, and also some static verification prior to program execution. This is our workflow for this presentation today. So first, we will present QAPL and how QAPL simulates quantum computation. Secondly, we will present the QAPLV, which is the integrator of QAPL programs, and along with the verifier. And also, we will show our perspective on correctness in quantum program. And lastly, we will present the future work on formal verification and APL. First, I will present about QAPL. So QAPL unknowns stand for Quantum APL. It's a quantum programming library written in APL. So basically, like we want to use APL because we want to explore quantum computing in both theoretical and practical side. We want to create a quantum software that people can implement at a high level. And secondly, we want to create programming languages that make quantum computer better and also prototyping the quantum computer architecture. QAPL abstracts like over quantum circuit patterns with several motifs such as structural and parameterizable elements. And we also want to have some verification motifs that this motive will lead to verification of programs. This is an example of how QAPL simulates a quantum circuit for random number generation. On the left-hand side, you can see the quantum circuit, and on the right-hand side, you will see the QAPL code simulating the circuit. In this circuit, we will have a quantum state containing 4 qubits. These 4 qubits will go through the Hadamard gate and it will turn to the superposition state. All of these 4 superposition states will be going through the measurement states and will be in the destructive state, and then we will measure and we will have the output from that. The random element stands on the Hadamard gate and also the measurement one. Secondly, we will present QAPLV and also our perspective of correctness in quantum programs. First, QAPLV also stands for QAPL verified. It's is an interpreter that will interpret the QRPL programs and also to verify the QRPM programs also. In this graph below, it is our perspective, and it's our vision to put QPL and QPLV into perspective. We want to have the QPL and QPLV to maximize the productivity and the program correctness in quantum programming. The reason that we want to do verification is that we want to push verification towards security and correctness at the start of the quantum technology, and to avoid poor programming language in designing practices like a null pointer. Secondly, we want to have a correctness to address scarce quantum hardware, because right now we have a very limited quantity of properly accessible quantum computers, and each time that we want to use any quantum computation is very expensive, about $2,000 to $5,000 per hour. And also we want to deal with noisy intermediate scale quantum hardware, because right now this quantum hardware is very susceptible to noise sources like mechanical from mechanical or atomic decay. So there's some errors in quantum, like a bit flips. So the bit flip there is also in classical, but in the quantum the bit flip error is more common. So right now I will present some formal definition of QRPL program. So some formal definition of QRPL programs. So a QRPL program P is a collection of statements to encode and transform classical information using the laws of quantum mechanics. So QRPL statements have four types: the vector states, the qubits, the quantum gate operators, and the projective measurement operators. Note that the operator in quantum mechanics differs from the operators in APL. This is some sample of some primitives that implementing in QAPL. So as you can see here, the Q0 and Q1 representing the base states, which will represent in the column vector. The dagger one will be the function that returns the complex conjugate of the input. The input can be a vector or a matrix. The normalized one, because we want the normalized functions, because we want to ensure that every vector to be in the inner size. So we want to create a normalized state in order to after any operation we can normalize the vectors down to have like a normal state. And also the QX, we will perform some kind of linear combination between these states. We also want to normalize it after, in order to have all of these qubit states to be in the unit size. Secondly, we have also simulate the block square, which represents the linear combinations between of any qubit state by the linear combinations of 0 and 1 in the base states of the qubit. And also, we have some non-parametric gates like the X, Y, and Z gates also. And we also simulate some parametric gates where we rely on several inputs, such as like a XX gate that we implemented over here. So this is some sample of some primitive that I have just represented to you. So next, we will have some correctness definition of QRPL program. So first, I want to define partial correctness in QRPL programs. So the first condition to achieve partial correctness is that all operators and functions in quantum mechanical parts in QRPL programs have to comply with the rules of quantum mechanics here. And secondly, condition to achieve partial correctness is that all of the pre and post conditions must be proved correct at both compile and runtime. we want to extend the partial correctness to end-to-end correctness. I know that some of you will ask, like, why do we have two ways of correctness, partial and end-to-end? So basically, the reason is that right now, the quantum software relies on both classical and quantum size. So basically, like, we want to have partial correctness to be ensure that all the quantum program to be correctness on the classical side, and end-to-end correctness will ensure that it will be combining between classical and the quantum sides. So that being said, so QAPL, so we will define end-to-end correctness. So a QAPL program, P is considered to be end-to-end correctness if P is partially correct that we have just defined. And also the outcome of P, and when it's running on the fault-tolerant quantum hardware, is the same as like the output of P when it's running on the quantum simulator on top of the classical hardware. And some fault tolerance properties that can be listed, that such as like a quantum computer has multiple physical qubits with a given fidelity, and a logical qubit is an error-corrected correction of physical qubits as will be ideally specified. And we also have some safety and liveness for end-to-end correctness. So LNS to be the set of safety and liveness statement of the P, and we want to have all these sets must simultaneously for classical and quantum environment when P is executed at all times T. Next, we will have some example of verification of the Dues-Josa algorithms. So the reason that we choose the Dues-Josa, because the Dues-Josa is the algorithm that will perform in constant time in quantum computations, that will ensure that a function is balanced or constant. And this function is very significant, so we really want to try to verify these algorithms. So from this on the left-hand side is the Dues-Josa algorithm implemented in QAPL, and this part of code will go through the QAPLV interpreter, and this QAPLV will interpret into the Python code, and then it will going through the Z3 SMT solver, where it will verify our invariance, our requirements about invariance, assertion of pre and post condition, and also some safety and liveness conditions, and it will return some SMT code for verifying this function, for verifying this algorithm. And some of the APL subset for some QAPL interpreter right now that we have implemented, such as data, we have implemented like integer or real literals, and also we have some array operations. In terms of functions, we also have arithmetic operators and the defans. And in terms of operators, we have some combinators and the reductions, and so also others operators as well. And lastly, we will have some future work on formal verification and APL. So some future work, we would like to extend verification to a larger subset of APL. So we would like to have quantum algorithm library will bring new complexity, and we would like to reuse the interpreter for APL programs in general. Secondly, we want to integrate ZX calculus to extend the correctness guarantees, because ZX calculus encode abstract properties of circuits, and also ZX calculus will reduce the complexity of the quantum circuits. Thirdly, we want to study the role of the safety of APL interpreters, where because the robustness of the language moves the problem into the safety of the interpreter. And lastly, we will integrate the quantum noise models to the verification process in order to test how verification will go if we have the quantum noise model. And lastly, we have some summary and takeaways. First, quantum program verification is facilitated by APL, Secondly, QAPL provides a compact, self-contained platform to study the impacts of correctness and program safety in quantum computing. And lastly, fault tolerance is essential to define program correctness for quantum programs, which contain both classical and quantum elements. I think, yes, that's it. Thank you.
Thank you very much. Do we have any questions? Are we going to get your cameras on? Great.
Hello, thank you for the talk. I remember Santiago's talk from last year's APL conference, and I'm wondering, I sort of asked a similar question at that time about the size of the current systems you're able to currently simulate. I mean, it's known that classical systems get an exponential blow up for most classes of quantum systems. So how big of systems and gates are you actually working with and have tested with this?
So right now we are at the beginning. So basically, we are trying to test some simple gates first. We are planning to have like a very enormous gates in the future. I think so.
I mean, what kind of sizes are you dealing with? Can you give just a few example numbers?
Sorry, can you speak that again?
What kind of, like, how many gates are you able to currently simulate on what kind of problems right now? Do you have some just examples that you might be able to say immediately?
So size. So let me just go back to this slide. So right now, we are trying to verify some of the X, Y, Z gates and also some X and Y gate on certain requirements that we have listed out. I know that there are some bigger gates that can be constructed, but right now we haven't tested or verifying on that.
Okay, thank you very much.
All right, thank you very much. All right, and I think that was the end. And so when does the reception City Hall thing go? 6 o'clock? So is it 6? Okay, so we should be walking over there pretty soon. All right. All right, thanks. My apologies for being a cough-tastic monster over here.
Looking forward to the workshops and the mailing list. Oh yeah. So we need to decide who's going to do the organization next year.